Hello, everybody. Welcome to Laws of Nature, to today's session about quantum foundations and the future of quantum foundations. I just quickly remind you about this initiative, which has been initiated by my colleagues Dirk Decker from LMU and Worstru from Leuven and myself from the University of Trieste. The idea is to create a platform to discuss about the foundations of quantum mechanics in a broad sense. I just would like to advertise once again our website, which you should see now, and also the spring series. So this is the last meeting of the spring series. We started with Roger Penrose about how the large and small interrelate in GR and quantum mechanics. Then we moved with mathematical physics and electromagnetism with Kisling and Wald. Last time we had discussions about quantum gravity with Francesca Vidotto and Stefano Liberati. Now we are happy to end this spring session with two young colleagues, Siddhant from the LMU and Sandro Donadi from ANFN here in Trieste. And this is also meant to be a tribute to two special people that are not with us anymore, but it meant a lot for us three and a lot also for the quantum foundations community. One is Giancarlo Ghirardi, a world expert in collapse models of spontaneous wave function collapse, and the other one, equally well known, is Detlef Dur, that together with Shelley Goldstein and Nino Zanghi gave major contribution to the appreciation of the mathematical and physical development of Bohme mechanics. And today, Sandro first and Siddhant later will somehow move forward the torch of quantum foundations in these two fields. And so I leave the floor to Paola to introduce the speakers, and I hope you will enjoy today's session.
Thank you. So welcome everybody to this last session of the spring series. Today's topic is the future of quantum foundations, and we have two younger people who will hopefully be working on this for the next several decades. And we have Sandro Donadi, who will tell us something about the collapse models, and Siddhant Das, who will talk about arrival time statistics. And before we go on, so we have two talks, each will be about 45 minutes, and after the talk there are 15 minutes to ask questions. And in the end, we have a general discussion for 1 more hour. So all the general questions we can then discuss in the end. If you have any questions before, so like in the talk, which are really urgent, then please don't interrupt immediately, but just write it into the chat, and I will then figure out if we have time to ask, then I will ask it for you. Okay, so actually we skipped the order of the talks. So the first talk today will be the talk by Sandro Donadi. He has been a PhD student of Angelo Bassi, who is here as an organizer. And he had now different postdoc positions in Germany also with Dr. Hossenfelder was the last, and now he's back here in Trieste. And has been working all the time on collapse models. So we will be happy to hear what you can say about the state of the art and the future perspectives of these models. So please.
Okay, can you see my screen?
Yes.
Okay, so first of all, thanks Paola for the nice introduction, and thanks to the organizer, first of all, to have organized this series of conference, and then also to give me the opportunity to talk about some of the research I'm doing, and as already Angelo and Paola mentioned, will be a talk mainly focused on collapse model, also in memory of Professor Ghirardi. And I will try to before give some introduction also for who is not too familiar with the model, to explain a bit what's the idea and how they work, then to give some state of art of the possible experiment that can be performed to test this model, and then some possible future development. So the starting point usually for me is always one slide on the measurement problem, because collapse model have been suggested exactly to solve the measurement problem. So the measurement problem can be summarized as this. In standard formulation of quantum mechanics, we have two different dynamics for the state vector. One is the Schrödinger equation, which is linear and deterministic, and the other one is the wave packet reduction postulate, or just collapse, which is nonlinear and stochastic. And the problem in quantum mechanics is that you have these two different dynamics, but the theory is not really clear in telling when one is supposed to use one or the other one. So in the postulate of the theory, you find words like observer, measurement device, which are not well-defined concept. And this has been pointed out by many people, among them also John Bell, which I would like to quote, because I think in this quote he put the problem in a very clear way, and he asked, what exactly qualifies some physical system to play the role of measurer? Why I cannot just treat it with Schrödinger equation, but something changed? And standard quantum mechanics does not provide a proper answer to this question. And several solutions to this measurement problem have been put forward. Some of them are like reinterpretation of the theory, in the sense that they lead to the same prediction of quantum mechanics, but actually solve the measurement problem. One example is Bohmian mechanics, which I will also discuss very briefly later at the end. But the solution I'm going to focus in this talk are collapse model. And the basic idea in this model is to say, okay, we have these two different dynamics, why we don't put them together? So the idea is to take the Schrödinger equation and to add some extra terms, so to modify it. And these extra terms are the one describing the collapse of the wave function. Of course, this needs to be done in a careful way, because we want that these collapse terms should be negligible when we have a microscopic system, because we know that in that regime, Schrödinger equation works well. But on the other hand, they have to become dominant when we move to macroscopic devices system. So I will start by introducing the GLW model, which was the first collapse model proposed in the literature, and also because I think it is in a way maybe a bit more intuitive than others. The mathematics also is a bit simpler. It does not have stochastic differential equation. And so this was suggested by Girardi, Rimini, and Weber. And the model works in this way. You have the Schrödinger equation, like in quantum mechanics. And then you have spontaneous localization, which affect any system. So here there is no word like measurement observer. The spontaneous localization are always there. And there are some rules for this spontaneous localization to happen. First of all, they happen at random times, but with a certain rate, average rate, which is given by lambda. And this lambda is the first parameter introduced by the model. And then the localization mathematically is described, for example, the localization around the point A in space is described by multiplying the wave function of the system with a Gaussian centered in A and with equal to this RC. So this RC is the other parameter of the model which set the spatial resolution of the model, of the collapse, sorry. And then we also need to give some rule for the probability of localization to happen around certain points. And this is basically the counterpart of the Born rule in this model, which is given by this rule. Now, let me show with a simple example how the localization happens. In case of GLW, I think is particularly intuitive. So imagine that you have some wave function, some system which is in a superposition of here plus there. And let's say that there is a localization around the point A. Then after the localization, because you multiply the wave function by this Gaussian, the final wave function will be much more peaked around A, and there will be only almost completely negligible around the other point. And if you look at the probability of a localization to happen around the different points, you can see that is almost equal to 1/2 around the 2 point A and minus A, but is negligible and basically 0 in point when the wave function is almost 0. So this is how you don't have conflict also with the Born rule. And well, regarding this RC, this spatial resolution of the collapse, there is now actually a fixed value, as we will see later on in the literature. More value are considered. But in the original work, Ghirardelli and Weber suggested this, which has become somehow a reference value also in the literature. And this is a good compromise because you still have a spatial resolution which is quite small compared to macroscopic distances, but it's still larger than the atomic size. So you kind of guarantee that the collapse does not disturb the structure of matter too much. Okay. Then, so one thing that a good collapse model has to do is to collapse in space. The other thing that it has to do is, which is actually how the models solve the measurement problem, is to have an amplification mechanism. And in order to show how it works, let me just consider the case of two particles. And let's suppose that they are in this state, entangled state. So I have either both of the particles on the left, so the whole system is on the left, plus being on the right. And then suppose that a spontaneous localization happened to only one of the two particles. Then the effect is still that after the spontaneous localization, only one of the two branches survived, which means that if we assume that, for example, the localization for the different particle happen independently, then you have a rate which is twice of the one you would have only with one particle. And then by extending this reasoning to a system of n particles, you can basically show that the collapse rate for a large object increase with a number of constituents. And this allows the following, that one can choose a value for this lambda parameter, which is the rate of collapse for a single proton, even quite small. For example, Ghirardelli and Weber suggested this value, which means if I have a small system in a superposition, the number of localization will be basically 0, will be 1 every million and million of years. But on the other hand, if you have some macroscopic object, so this n, for example, you take Avogadro number, then you have almost instantaneously localization. So even if you have a cat which is dead and alive, it will not stay for more than a small fraction of a second. So this is how, thanks to this amplification mechanism, you have one dynamic, and automatically these dynamics reduce to the Schrödinger equation with an excellent approximation for a small system, but to the collapse when the system involved is large. Okay, that was the GRW, but the model which have been more largely considered, even in view of experimental tests, is the continuous spontaneous localization model. In this model, contrary to the GLW, where the collapse happens as a Poissonian process, so you have Schrödinger, then a collapse, Schrödinger, then a collapse. Here the collapse is continuous and is driven by a collection of Gaussian linear processes. Well, also you see, you don't have the full postulate, but you just have one stochastic differential equation which describes the dynamics. So in this equation, we can see, okay, the Schrödinger term, which is the standard, and then the other two which describe the collapse. And it's important to notice that, okay, there is an element of stochasticity, and there are these non-linearities. This bracket means you take the average value of this mass density operator mu on the state psi. No, you need both of these features. You need the non-linearity because otherwise you don't have real collapse. And you also need stochasticity because if you build up a dynamics which is non-linear but deterministic, then this can be used to do faster than light signaling. There is a theorem due to Gizen which proves this point, you just have to create then an EPR-like setting, and then a nonlinear deterministic dynamic would allow Bob to know which measurement Alice is performing. So this is also why you need stochasticity, and also because the outcome of quantum mechanics are also stochastic. Now, this is a collection of linear processes, one for each point in space, and they are correlated in space with, again, with this Gaussian. So as you can see, there is also the lambda, which was also before in the GLW, which somehow is the coupling constant of this noise, and this RC, which set the correlation of the noise. And indeed, CSL is connected to GLW, and one can see this, for example, when writing the master equation for the two model. For a single particle, the two master equations are the same. But at the level of collapse, they describe the collapse in a slightly different way. Now, one reason why also CSL become also more popular is that it was built in the second quantization formalism, and so this allows to treat also identical particle. It localized in space, and there is also here an amplification mechanism is slightly different compared to the one of GLW, in the sense that the amplification sometimes can go quadratically with the number of constituents, which is also important when you want to do prediction and test with experiment, because having an n square instead of an n can make the difference. But the important part is to have an amplification mechanism from a conceptual point of view. And also, this is the master equation of a model, which I thought is good to report. So for who is also more familiar with the open quantum system, as you can see, the Limblad master equation, because the model is Markovian, because here we have linear processes. There are also no Markovian extension, but I'm not going to cover this today. So up to date, I mentioned about the fact that this model can be tested experimentally, and the reason is exactly the fact that you have this additional term, and so they do different prediction compared to quantum mechanics. And let me enter a bit more in detail on some of the relevant experiments. Even here, there is no time to see all of them, but I try to take some collection of the ones which I think are significant. So the obvious way to test a collapse model would be to do interference experiment. So you do the interference experiment, and then you see if the interference pattern is still there as predicted by quantum mechanics, or it is destroyed by the presence of the collapse. And because the effect of the collapse grows with the mass of the system, the larger is the system you use to do interferometry, the easier it is to see this collapse effect. Now, in this respect, the record is kept by this the group of Markunsart, which recently they did this experiment with a particle with masses of almost 10 to the power 5 atomic mass. But as we will see, actually, this kind of direct test of superposition principle are not really the best way to test this model. They can set some bound on these two parameters of the model, but the bound are kind of weak. One can do much better exploiting another feature of the collapse and sort of perform what I call this indirect test. So the thing is that this extra term that one adds, or if you want at the level of master equation, this Limbladian, they don't only implies collapse in position, but they also implies other effect, and in particular a random motion which is induced by the noise to the system. And this is bad even for well-localized system. So this allows somehow to try to look for the existence of this noise without having to create a superposition of massive particles, which is not easy, and you have to maintain them. And basically this idea has been considered a lot in the last, I would say, 7-8 years. And one possibility, for example, is to use cantilever. So the position of the sphere using a laser and optomechanical device can be studied in greater detail. And so if there is some additional noise due to the collapse, this should be seen by studying the position of the sphere. Another way is to consider cold atoms. With cold atoms, one can also do cold atom interferometry, which is also being considered, but this is not what I'm talking in this part of the slide. Here I'm talking about an experiment done by Kazevich group, where they were able to cool down a gas of cold atoms down to picokelvin temperature. So as you can imagine, when you reach that kind of temperature, then even a small noise in principle should be detectable. And so this can also be a possible way to test collapse effect. One more recent test was possible bound were considered by this neutron star heating. Again, the idea is that neutron star, if the collapse effect will be really strong, should be hotter than what we observe. With the same line of reasoning, there is also the gravitational wave detection. For example, when you consider the LIGO experiment, and there are these huge mirrors, so they are really macroscopic objects, but which position can be known with high precision, otherwise you will have not seen the gravitational waves. And this again can tell something on whether or not there is this collapse noise. And finally, there is this radiation emission, which is one of the topics I know better, because when I started the PhD with Angelo, I mainly focus also on this. And again, here it's easy to think about it in semi-classical terms. So if you have a charge system which is interacting with an external noise, the noise agitates the system, and then because it's charged, it will induce emission of radiation. And this is basically some radiation that, according to quantum mechanics, you should not see. So one can do experiment in proper environment. In particular, we did in these underground Gran Sasso laboratories, and they can set also important bound on the strength of the collapse. So this was just an overview. There are also other proposals, for example, using rotational decoherence, but I don't have time to follow all of them. But the idea is always about detecting this jiggling, this motion induced by the collapse. Now, let me just show how these different experiments then convert in bound on CSL models. So there is this plot where on the x-axis there is RC, which is that correlation length, the spatial resolution of a collapse, if you want, and this lambda, which tells you the strength of the collapse. And this is the value suggested by Ghirardelli and Weber, which I mentioned also before. There has been also another couple of range of values that was suggested by Adler, which was arguing that probably collapse should be actually stronger than what considered by Ghirardelli and Weber. And here there is this gray area, which here I wrote theoretical, because so this area, it has been excluded not by any experiment, but by theoretical reason. And the logic is the following. You create a collapse model because you want to solve the measurement problem. But if a collapse is too weak, then it's useless, because then it will not be able even to make collapse, I don't know, a chair, because if you take lambda equal to 10 to the power minus 50. And which is why then you can exclude some combination of this parameter when they make the collapse effect too weak. In this case, this area was excluded by considering a graphene disk, which was the smallest object one can see with a human naked eye. So this was taken as a measure of macroscopicity. This is a bit what one can disagree. One can say that macroscopic it meant something a bit larger, and this is This is fine. That will put down this boundary, but I think this is a reasonable figure of merit. And now let me go to the experiment. So this is the parameters which are excluded by the matter wave interferometry. Then if we consider the cold atom expansion, it excludes a bit more, and also if you go for smaller RC, this line goes down even more, so the region becomes larger. Then the neutron star heating, and then the X-ray emission, which is currently the best bound on this side of the parameter space. On the right side, there are the gravitational wave detectors. So we have Auriga, LIGO, and LISA, which in the order put stronger and stronger bound. And then at the end, I report also the cantilever, the most recent experiment from 2020, which exclude also all these areas. So we are still left with a square in the parameter space, but somehow we are slowly reaching down to GLW, or even would be even better to exclude everything. But I mean, these each box is 2 orders of magnitude, so it will still take some effort to exclude all the parameter space if it has to exclude or to find something new. Now in this respect, I wanted also to discuss about some possible improvements, some possible new way to test the model. So of course, one possibility is to do this experiment I have already mentioned in a better way. But another one, which it has been considered in the last 5-6 years, I would say, is to go to space. And why to go to space is interesting. I mean, there are many reasons, but by far the most important is that in space you can put a particle and let it there for up to 100 seconds without the problem that it falls on the floor and then you lose it. So you can really leave the system completely free with nothing disturbing it for long times. And so this gives more time for collapse effect to build up and then might make them more easy to be detected. Let me also say that this kind of experiment is not only interesting for collapse model, the one in this picture, because this is an interferometric experiment. And the expectation is to go to masses up to 10 to the power 11 atomic mass. So this would be interesting even just as a test of quantum mechanics, of the superposition principle to this kind of masses. Well, since the current record is 10 to the power 5, this will jump to 10 to the power 11. And the interferometric experiment is done like this. So before you trap the particle with some optical trap, you cool it down, and you wait some time so the wave packet can spread enough to be larger than the slit distance. And in this case, it's important to have a lot of time, because the more massive is a particle, the less the wave packet spread. It takes more time. Then you use a laser grid. So instead of a matter grid, because with this large object, matter grid will stop too many of the particles, will create noises, problem. So they found out that using a laser grid is better. And then you switch it off, you wait, and you see after some time you measure the position and you check whether there is interference or not. And well, we did some estimation of how this kind of experiment should, which kind of bound can set on CSL. And here I'm referring to the left figure. The results are encouraging, because this brown area is already excluded by masses of 10 to the power 7, so not even so huge. And then if you go to 10 to the power 11, you have basically this orange line. And so this might be really relevant for testing the model, but as I said, also as a general test of superposition principle. Yeah, there are many details to say actually, but I don't have time. But yeah, there are some assumptions on the kind of pressure you can reach, the kind of time. So all the numbers that have been used are kind of reasonable. It was not stretched. On the right, I also report the bound expected from a non-interferometric experiment, again in space. In this case, what do is something even simpler than before. You trap the particle, then you switch off and you trap it only to cool it down, because it is in space, so it does not fall. Then you switch off the trap and you just wait. And according to CSL and general collapse model, for the free particle, then the variance will increase. But of course, it will increase also according to quantum mechanics, but then there will be an additional contribution, which goes as the time to the power cube. And so in this case, again, having a long time can be relevant, and this will also set some bound on CSL. The continuous line is the bound, assuming pressure of 10 to the power minus 11 Pascal, the dotted lines if you can go to 10 to the power minus 14. But anyway, I just think that in general, this idea of testing in space can be important, and even beyond quantum collapse model. I mean, if you want more information about these ideas, Macro was one of the first approaches, and then there is the cost action QT space who studied this a lot in collaboration also with Visa. So this was all about CSL. Okay. Now, I would like to discuss about another important collapse model, which is known as the Diosy-Penrose model. So in this model, the idea is to relate the wave function collapse to gravity. And actually, Penrose and Diosy arrived to predict the same time of decay of a superposition, but the reasoning they did was very different. And so I will start by quickly reminding the one of Penrose, but if someone is really interested, I strongly suggest to go and check the first of the seminar of this Laws of Nature series, but Penrose himself is talking about it, so it's much better. So the idea of Penrose is this one. So suppose that you have a mass in a superposition, then this of course will also induce the superposition of different curvature. We will curve the space time in different way according to whether the mass is centered around the point A or B. And then Penrose provided some argument. For example, the most recent is some conflict between this superposition of different space-time and the equivalence principle. So he provided argument as for why this superposition should not be stable if this difference between the two space-time is large enough. And it gives a formula to compute this difference quantitatively, which is given by this delta E, which is a formula for Newtonian limit, where basically you consider the Newtonian self-interaction of the difference of the two mass density, one when the particle is around A and one when the particle is around B. And then given this quantity, which has the dimension of an energy, one can compute a time of collapse, which in a similar way of what one does in, for example, in nuclear decay. You take h bar divided by the energy and you get a time. And if one try to plug some number, they are encouraging, because you see that for a proton, for example, the time of collapse of a superposition would be of order of millions of years. But if you take a dust grain of order of 10 micrometers, so not even a huge object, the collapse is basically instantaneous. This is 10 to the power minus 8 seconds. So then, before this proposal of Penrose, Diosy already put forward a collapse model which was related to gravity. And if you remember the equation I showed before for CSL, it was extremely similar to this one. So the idea of Diosy was, okay, we know that collapse equation has ought to have this kind of structure, but why instead of adding new parameters, we don't try to relate this to something we know, which is gravity? And so he took a collection of linear processes, which correlation is given by this Newtonian potential instead of the Gaussian, like in CSL. And then given this master equation, one can compute the, given this equation for the state vector, one can compute the corresponding master equation and then check how the off-diagonal element will collapse. And you find out that the time of collapse is exactly of the same form of the one suggested by Penrose. Maybe apart from some factor of pi, but it's not important. The relevant thing, and this is the reason why the two things, despite coming from very different reasoning, have been put together in Diosy-Penrose model, because they lead to the same time of collapse in the case of a simple superposition here plus there. Now, there is a problem with this integral, and it is related basically to the fact that here we have this Newtonian potential. And then if you consider a point like mass density, sorry, I didn't mention, but this is the mass density mu, then no matter how small is the mass, even for an electron, this will diverge the integral, which means basically tau will be 0. So this is clearly absurd because it would mean that you should never see quantum effect with electron, which doesn't make sense. And this is also why you need to introduce some cutoff, some parameter which describe the size of your mass density. And this is what I will refer also later as R0. Now, what about the test of Joseph-Penrose model? Again, you can do direct or indirect test, but so the direct test, there has been many interesting proposals. The first one came back to 2003 and was also one of the articles starting the optomechanics, was Marshall, Penrose, and others. And basically here the idea is to have this laser hitting of a photon hitting on a crystal many times and putting it in a superposition. And I think it seems possible that in the next years also this experiment will be actually maybe performed. So it will be quite interesting. More recently, there has been a proposal using Bose-Einstein condensate. And then there is no proposal with proper calculation still done, but from a bit of some estimation we had done, I think that also the experiment in space that I discussed before might also be relevant for testing interfere directly the Joseph-Penrose model. However, up to date, these tests are still not possible to be done. So what one can do is again to try to do an indirect test, especially if you consider the Joseph version of the model. Then you have the master equation, and then this implies that you have all these heating effect, all these things that we have been also exploited for the case of CSL. And in particular, the kind of indirect effect that I'm going to discuss here is the one of radiation emission. So let me start before explaining very roughly how it is the theoretical calculation. So the idea is to compute the radiation emission rate, which is defined in this way, and the tricky things, that the hard part is to compute this, which is the number of photons emitted at time t with a certain wave vector and polarization. And the way the calculation was done was starting from the adjoint master equation and then treating perturbatively the Lindbladian, which is basically related to the collapse, and then also the electromagnetic interaction, which is inside H. So H includes system, free radiation field, and interaction. And the calculation is long, but is not conceptually, there is not conceptual difficulties, it's just long. And at the end, what we found is that the emission rate for a crystal is given by this formula in this red box, as long as the wavelength of the photon emitted is in this range, these quantities are Armstrong. So, sorry. Let me just comment a bit about these equations. Okay, we have the standard constant. Then we have R0, the size of this mass density, which also enters with the power cube. So it's an important factor of this cube. And then we have that the emission is proportional to the number of atoms in the crystal, which is quite reasonable. But also it grows proportionally with the square of the atomic number. And this is basically because the atomic nuclei are emitting as if all the proton in the same atomic nuclei are emitting coherently, and this is the reason why you have this n square enhancement. And the formula should be used in this regime, because if you go for smaller wavelength, you will not have coherent emission from protons, and more importantly, you also start to go in relativistic regime, so the whole model is not valid. If you take larger wavelength, what will happen is that the emission from the nucleus of an atom and the one from the electron will cancel each other. And so then you will not see any effect. So this is the best range of wavelength to get this effect. Now, about the experiment. So the experiment was performed at the Gran Sasso underground laboratories. This because the emission rate is extremely low. So you want an environment which is as clean as possible from external noises. And here you have a 1 kilometer mountain covering the labs. The setup is something like this. I mean, this is a simple picture, but so the green one is the germanium crystal, which was the one of which we measure the radiation emission. And all around there are some sheld of copper and lead to further protect it. And this histogram is the collection of data collected in 2 months. So in 2 months, the total count number of photons emitted was in this range of energy, which correspond to the wavelength I mentioned before, was only 576, which is very low, is less than 10 photons per day. And out of this, 506 could be explained using a Monte Carlo simulation, which was accounting for the known process, which also can induce emission. So this further improved the result. And then basically by comparing what this measurement with the theoretical calculation, you can set a bound on this parameter at 0, which must be larger than 10 to the power minus 10 meter. And well, this bound turned out to be even better than others that again were set using this indirect effect of gravitational wave detector and neutron star. And also it clearly shows that this at 0, it cannot be of order of femtometer, which is what one would expect for a proton size. And also it cannot be of the order of this at 0, which is this value here, which was the one suggested by Penrose, which was taking as a size of the mass density was related to the wave function of the system, the wave function of the atomic nuclei in the crystal. This turned out to be still 10 times smaller than the limit it was put. So in this respect, if one assumes a dynamical collapse, and in particular here it is important, is a Markovian dynamical collapse, then you need somehow to introduce this parameter at 0, which is not connected to any mass density or also any gravitational things. Alternatively, one can try to introduce some non-Markovian effect that may reduce a lot the expected emission rate theoretically. Or one can try to do even better, so to introduce maybe some different framework also to try to avoid this heating effect. And this is what also Penrose mentioned again in this talk. Or, and this is the direction I actually more interest, would be to try finally to understand something more about this noise in collapse model. Until now, we just postulated it, but it would be nice to start to give some physical structure to this noise, so then we can also associate some energy. And then once you know how to compute the energy of the noise, you don't have any more this non-conservation of energy, because the overall energy of system plus noise would be conserved. And with this, I go to the very last part of the talk. I'm close to finish. And well, I'm talking a bit of Bohmian mechanics, which might sound a bit strange at this point that I talk of collapse all the time. But it will be clear in one slide why I'm introducing Bohmian mechanics. Well, I think most of you are familiar with Bohmian mechanics, and actually much more than me, many of you. And well, in this theory, basically you don't just have a wave function like in standard quantum mechanics, but you have real point-like particle which moves in space. And this is also how this approach solves the measurement problem. And the trajectories of this particle is guided by the wave function and they follow this guidance law. And this is a very famous picture which shows how Bohmian trajectories can reproduce, for example, the result of the two-slit experiment. Now, why I'm talking suddenly about Bohmian? Because there is a connection with collapse model. The moment you consider more than one particle, and you have to keep things simple, I will just consider two, then you can define an object which is called conditional wave function. So you take the wave function for the two particle system, and then you replace the y variable of the second particle with its trajectory, and then that this is really a wave function with norm 1 with respect to x. Now, the interesting things of doing this is that this conditional wave function in general does not follow the Schrödinger equation. And let me try to give some intuition why this is the case. So, suppose to have two particles, but the state is a separable state. Then you can define the conditional wave function and nothing really interesting happens. The conditional wave function is exactly the same as the function here. If, however, the two particles start to interact and then the state become entangled, and let me suppose, to keep things simple, that the state of a second particle is basically a Gaussian which is centered at different points, YA or YB, depending which part of the superposition of the X particle interacted with it. Then when you have this state and you compute the conditional wave function, and let's say that you're considering one of the trajectories which goes around the point YA, so big Y is more or less equal to YA, then this makes this exponential equal to 1. And this one is basically 0. And sigma, I'm assuming, is much smaller than the distance between these two. And what you have is that the conditional wave function is just one of the two parts of the initial superposition. So this is really quite similar to the GLW collapse I described in one of the first slides. And so it's interesting that here we have a connection with collapse, and here there is no an external noise. It comes from the interaction with other particles. And yeah, well, in particular about the connection with GLW, we did a work some years ago with also Marco Toros, me and Angelo. But more recently, there has been a nice paper. I still have to read it in detail, but it looks extremely interesting from Tilwa and Weisman, which show connection between non-Markovian collapse model and conditional wave function. I think it's something interesting to explore more in detail. Okay, and finally, and this is more just an introduction to the next talk of Siddhant. I just want to briefly mention about this arrival time problem, which is basically one asks, given a particle and given a screen, instead of asking, as you do typically also in the two-slit experiment, you look where the particle arrives. But what if you ask when the particle reaches the screen, when the detector clicks? Well, the usual recipe of standard quantum theory that you have to take the observable, the relative, the corresponding eigenstate, you project the state on the eigenstate and you take the modulus square. Here does not apply because you don't have an arrival time operator. And so several possibilities have been suggested in the literature. And what Siddhant will talk about it in large detail, but I mean, for example, Bohmian mechanics provides some possible suggestion for a definition because of the presence of trajectories. I think also collapse model might tell something for large enough particle, because in that case you have always localized wave packet moving in space, while for a small particle is more tricky. Then I think you have to really describe also the detector in detail. But independently of Bohmian collapse, I mean, I just think that here the question is clear, and this is an observable quantity. The detector click at some times, and so if think it should be found a way to compute this quantity and to deal with it properly. Okay, and with this, I just summarize this at the conclusion. So we have seen that collapse model modified the Schrödinger equation, adding this stochastic and nonlinear term which describe the collapse, and that there are several experiment setting bound on this model, and probably also going to space in microgravity environment can help a lot. And finally, there is this interesting connection between collapse and conditional wave function, and my hope is that this might also help to understand, to provide some framework to give an origin to this collapse noise, with more related to other particles interaction. So, okay, this is it. Thank you.
Thank you, Sandro, for this very nice talk. Yeah, I'd like to open it up for questions now. So if you have any question, please raise your hand, and then we call you and you can ask. So Aurélien Dressé, you just raised your hand? No.
Yes, in fact, it was something to find out. But I can ask a question because I have one in my mind. So I have a basic remark about Bohmian mechanic, because in Bohmian mechanic, in version of David Bohm for photons, for the quantum field, you have very curious feature because the field is completely delocalized compared to fermionic fields. And sometimes when you watch it correctly, you can interpret it as a collapse, because when the photon is interacting with, let's say, two fermions, it looks like a kind of collapse, because the wave functional is very complicated. The field is the photon field is very delocalized, and only one of the two electrons is detecting it. And so you have something which is, for me, looking like a kind of GRW, but from the Bohmian point of view. It's kind of, yes.
Is this a conditional wave function or is something else?
It is the idea, you know, in a very old paper of Bohm in '52, in an appendix, and he wrote this theory where the photon field is described by the degree of the quantum oscillator. It's not the particle is not the photon is not a particle; it's a field. But the behaviour are fields. But the fields is completely delocalized compared to a particle. So when it's interacting with a localized object like a fermion, which is described by a particle, then you have a curious feature, because one is continuous, the second one is discontinuous. So it leads to curious feature when you watch this in detail. So, and for me, it's a bit like a collapse.
No, okay, thank you. No, I'm not familiar with this, but maybe later if you can put the article link.
There are a lot of them.
Thank you for very much.
Okay, thank you. So we have the next question by Lorenzo Marcone.
Yes, I'm curious about this Penrose argument that there is a contradiction with equivalence principle if you have a superposition. How does it work?
Yeah, so as far as I understood it, basically, when you describe basically a system in a frame of reference where it can feel the gravitational field, or on the contrary, you describe it in the free fall, then the solution of the two-wave function are not the same, but they differ by a term, which is a phase proportional to t to the power cube. And if I well understood, the argument is that this is a kind of reminiscence in this non-relativistic limit of basically having two different Hilbert space referring to two different vacuum. And therefore, the argument goes saying that you cannot make a superposition of between state belonging to two different Hilbert spaces. This is as far as I understood it. But
no, I don't get it, because if the particle is in two positions in superposition, it always interacts with its own gravitational field, which is located at the particle position. So I don't understand what you're saying. In other words, the gravitational field just becomes entangled with the particle. So it's in the same location.
No, but wait, now I have to recall it, because I think the idea is that you have, on one hand, the particle in a superposition, which
Yes.
then will generate a superposition of two gravitational fields.
Yeah, exactly.
Then you have to imagine to put a test particle at a certain point where the gravitational field generated by one branch of the superposition is, for example, pointing in this direction, and the other one is pointing in the other one. And then, because you have these two different possible acceleration, you cannot find basically a free-fall system for this test particle. And that is where basically the problem arises.
So you need an
I have to
external
say,
gravitational field.
what?
Okay. So you need an external gravitational field. That's what
No,
you're
so
saying.
the gravitational field that becomes problematic is the one created by the superposition. And then you imagine to put a test particle inside this superposition of two gravitational fields. But I admit that I don't remember the whole argument in detail, but was something along this line. In the paper I mentioned here, I think I remember was written in a quite clear way. This one of 2014 Foundation of Physics.
Okay, thank you.
Thank you. So we have one further question by Dipankar Home.
Hello, Sandro. So you made a remark about the stringent bounds on the collapse models from non-interferometric tests in microgravity situation. There was this comment made by you. So is this related essentially to the wave packet spreading the noise in the collapse model, giving rise to some extra effect in wave packet spreading st to the power cube you mentioned? So
yeah,
that is related to probing the nature of noise in the collapse models. So that would be important from that point of view also. Is it essentially measuring the spread of the wave packet?
Not exactly the spread of the wave packet.
But what type of test that will put a stringent bound? You mentioned in one of your slides about the wave packet spreading going st to the power cube.
Yeah, this one.
Model. Yeah.
Yeah, this one. But actually, I don't know, maybe I was not fully clear. This actually is not really setting the strongest bound. The interferometric one is much more efficient in this case, because then you have always to compete. You don't have only collapse model noise. If it is bad, you have also the coherence due to collision with the particle, with radiation field. So it's not so easy to set the bound. And now what grows as t to the power cube is an extra term in the variance. So because on each realization, on each experiment, what collapse model does is to shrink your wave packet. But the point is that the point at which the wave packet will localize, will arrive at the end, will change. And that is what you measure and that is what grows as t to the power cube. But this t to the power cube actually is not really, setting still a quite good limit, but the most promising in space seems to come from this interferometric experiment, which is basically this one. While the one of t to the power cube, you didn't have the laser, you just let the particle.
So this interferometric, what advantage it has in space means?
Mainly this one. There are several, but I would say the main one is that you have more time. So more time means that two things. On one hand, collapse effect have more time to build up and to disturb your interference. On the other hand, also you need it because if you have a particle with a large mass, it takes longer for the wave packet to spread, and you need that it spread, otherwise if it's smaller than the distance here between the slit, you cannot do even without collapse model, you cannot do interference.
Okay.
So, but I would say definitely is the time that on Earth you cannot have a free particle for 100 seconds.
Okay. So it is basically matter wave interferometry over a long time.
Yes, exactly.
Okay, thank you.
Okay, thank you. I think it's already time to move on to the next talk. So, well, there's one more question in the chat by Aaron. I will read it to you. So the question by Aaron is, do you personally think that collapse models are a candidate for a really fundamental theory of nature? Or do you see them as effective theories?
Definitely effective. Yeah, I think at least they are consistent because they don't use funny words like observer and all these things type of stress. But there is this noise which is still put by hand, and this is what I think now we should try to improve also this aspect and to try to really find some origin for this noise, and then this might lead to something more fundamental. It will not be easy, but I think it's worth, and in some sense this conditional wave function might help. I don't know exactly how yet, but here you have this collapse which is not anymore coming from some external field, but is really related to the presence of other particles. So for example, if the collapse is really given by this interaction with other particle, then if I have a particle completely isolated, you will not have this collapse having this heating effect as predicted by CSL, for example. So, but yeah, I still don't know what is the direction, but I think we should try now to go a bit further than the phenomenological description.
Okay, thank you. So thank you again for your, yeah, Aaron agrees. So thank you again for your talk. And now we move on to Siddhant's talk. So Siddhant Das is now giving the second talk, and he is a PhD student in Munich at the LMU. And he used to start as a PhD student of Detlef Dürr, actually, who died at the beginning of this year. You all know that. And now he stayed at the LMU and works with Dirk and continues his PhD there. And he works on arrival times or time of flight measurements, which is, I think, a very up-to-date topic. And he will talk about the different theoretical predictions which exist in the literature, and also about an experimental setup he has in mind to test these different predictions. And yeah, so we're very interested in that, Siddhant, so please go ahead.
Can you see my slides?
Yes.
Yes, that's good.
Okay, and can you hear me well?
Yes.
Okay, so thanks a lot and welcome. First of all, I'm very overwhelmed to really see so many friends and colleagues here, and thanks so much for coming. For those who are wondering what the 2026 means in the title, I already got a couple of messages. It actually signifies 100 years of Schrödinger's first wave mechanics paper. This is the paper where, for the first time, I think the time-independent Schrödinger equation appears, and you also have the correct calculations of the hydrogen energy levels. And in 2026, we complete 100 years of this development, and that's a extremely important landmark for quantum physics, in my view. And I'm going to describe a particular problem, which already Sandro and others mentioned in briefly. And I think it's a really pressing problem for a successful theory like quantum mechanics. And setting 2026 as a goal for resolving it seems quite fitting to me. And I hope you guys will agree with me by the end of this presentation. Next, like Paula said, we are still recovering from the loss of our beloved mentor and father that left Earth. There are just so many things one can say about him, but one thing that always struck me in the time I spent with him, almost 5 years, is that he definitely pushed you to be passionate about science, but more than that, I think he also said, don't be irresponsible about the science you do. And he taught us in many ways how to go about it. And this talk is my joint work with him. He has contributed to it in many deep ways, and you will, those of you know him, you will see elements of his insight in many of the things I will present. All right, so let me dive right in and tell you what an arrival time experiment is. It's sometimes called a detection time experiment, a time of flight experiment, different names, but it really refers to a single particle scattering experiment. So you could have in mind things like double slit. That's the quintessential quantum mechanics experiment. Arrival time is in that ballpark. So it's a single particle scattering experiment, and the particle in this experiment is prepared in a definite quantum state at time 0. It's then allowed to propagate, and for all practical purposes, it's propagating freely. But if you want to be general, you could allow it to move in the presence of external fields. And then there is a detector whose surface I denote by S here. And, like the scintillation screen in the double slit experiment. And I hope everybody will agree that at some later random time, tau, you see a click on the screen. And in an arrival time experiment, you're interested in the statistics of these clicks, basically the time instance at which you observe the clicks as you repeat the experiment exactly in the way I described again and again. So I hope that's the starting point, and I hope it's clear to everybody. A bit on logistics. Of course, at the end of the day, the central object of interest is this P of tau, which is a probability density. It's the distribution of arrival times. So after you do many single particle experiments, accumulate statistics, this is what you would get empirically. And in theory, you are also interested in predicting this quantity. It has, as the name suggests, it has this obvious interpretation. So this P of tau, d tau, where it's a small time interval, is the probability that the particle was detected in this experiment between time tau and tau plus d tau. And this immediately suggests the kind of normalization I have put here in the box. So this logistics is common to whatever theory you want to use at the end of the day to predict this quantity. You would at least like it to be a respectable probability density. There is this P infinity written here. I will say more about it later, but it's actually added here to account for the fact that it's not necessary that the particle is detected in every run of the experiment. There could be various reasons for which the particle was just not detected, and you would have no way to define the arrival time, even experimentally in such occasions. And this P infinity is the fraction of experimental runs in which the particle was not detected. All right, so with this sketch, I would say our job, which basically here refers to theorists, is to predict this quantity P of tau given an initial state psi 0 and the geometrical surface of the detector S. One thing I would like to emphasize here, if you step down even from a quantum mechanical perspective, as I have set it up, it's a quite difficult problem, even for a theorist using Newtonian mechanics. I mean, just imagine for Newtonian mechanics, you have to follow essentially all possible trajectories of a particle as it is propagating towards the surface. And you have to discuss the statistics of the times at which these trajectories are striking the surface of interest. That's a very hard problem, even if you could solve for the Newtonian trajectories exactly. So by this, I want to tell you that you shouldn't be totally surprised if quantum mechanics also finds this problem hard. All right, so this is a picture I always love to show. This is experimental data from 96, 97, and it's from the group of Tillman Fao at that time. This, I mean, the picture on the left, of course, is ubiquitous in textbooks and everybody understands what it is. It's the interference pattern from a double slit experiment. What's interesting is the picture on the right. The data that's plotted on the left and on the right were collected in the exactly same experiment. And the picture on the right has the detection time or the time of flight on the y-axis. This is something you don't get to see very often. I don't think there are that many presentations of this piece of information in the literature. But the point of showing you this is to tell you that, look, this is something that has been measured, and it's not, I mean, okay, I have difficulty in expressing that, people sometimes come up and tell me arrival time is not an observable. And I think by showing this picture, at least, we gain a bit of benefit of doubt, if not more. Anyway, moving on. If you look at the literature, there is really no theoretical consensus on what this P of tau should be. And I will discuss some approaches. There are many of them. I mean, I guess near about 20. And given the empirical successes of quantum mechanics, and I should really clarify here that when I say quantum mechanics, I really have in mind the textbook quantum mechanics, where there is an explicit cut between the system and the apparatus. The apparatus is classical, the system is quantum, whatever that means. But that's the textbook picture. If you like, have Landau-Lifshitz in your mind, that's the quantum mechanics I'm referring to largely. And given the successes of quantum mechanics, this is particularly striking because the experiment is extremely straightforward, as I have just discussed. So this talk will cover theoretical candidates as well as a systematic scheme of experiments to distinguish one from another. I have already indicated how come such a seemingly straightforward experiment be a matter of an ongoing debate. And I would read out to you some statements from physicists over the years. Pauli was certainly one of the first guys to take note of the problem of not being able to discuss timing of events. You find his comments in letters to Niels Bohr as early as in 1925. But in 1933, he makes this remark in a footnote, which nowadays has come to mean time is not an observable. I don't think he said it exactly this way. He probably said time as an observable should be abandoned or something like that. Then there is a couple of years down the line, there is Alcock, who wrote a series of 3 articles on arrival times, and it has a lot of great material and new ideas. But at the end, he more or less concluded wave mechanics cannot accommodate an exact and ideal arrival time concept. Then there is further down paper by Aharonov and other well-known colleagues who said time of arrival cannot be precisely defined and measured in quantum mechanics. Well, by the way, that footnote is also very interesting. So this Pauli's result did give people reason sometimes not to work on this subject or even to ridicule the importance of studying time measurements. And this footnote here says this observation of Pauli had the effect of practically stopping studies on this subject for about 40 years. And I think there is some truth to that. Anyways, the literature is barely recovering from that. Meanwhile, experimentalists have been measuring time of flight, as they call it, basically all along. And time of flight measurements have become the quintessence of many standard experimental techniques of atomic and molecular physics. And I've just listed a handful of them. You know, if you have to measure particle masses, if you have to measure momentum in scattering experiments, all of ALHC, like most of LHC, let me put it that way. And these acronyms here are, you know, I don't want to give full forms. This stands for different kind of recoil ion momentum spectroscopy techniques and so on. Then there are papers where people have tried to reconstruct Wigner function from arrival time data. People have tried to measure absence or I mean, they have tried to check if the atoms emit spontaneously or they don't in certain environments using time of flight measurements. Then there are ways to access the band structure of solids using time of flight measurements. And then studying chemical reaction dynamics on literally the molecular level and so on. That's all right. And the literature abounds on measurements of this kind. Now, given that the theory has so much trouble discussing arrival times, one can wonder what kind of ideas do experimentalists put in to interpret their measurements. And if you read the papers, it's largely Newtonian mechanics, semi-classical heuristics, or even geometric optics. So it's, for all practical purposes, really not quantum mechanics as we read it in a quantum mechanics textbook of today. So there are only two things I have to say about this. First of all, uncritical reliance on, you know, heuristics definitely risks inconsistency. The second thing I want to say is that this, let me say, this unreasonable effectiveness of heuristics in the laboratory time of flight measurements has unfortunately distracted from giving a first principles description of arrival times within quantum mechanics. Okay, so what's the current situation? As I said, there are about 20 proposals. I mean, 20 is a bit arbitrary number. I guess maybe tomorrow there will be just a new one. But one thing is, some of them are rather difficult to compute. I mean, the mathematical machinery is somewhat involved. So it's hard to compute detailed predictions, even if you come up with a setup and contact some experimentalists. And given all this, it's not very surprising that experiments designed to test them have been slow in coming. All right, so with this sketchy preamble, it seems like we have a clear program, right? Collect all these options, calculate them, and just go out and check who describes the data better, who doesn't describe the data better, and so on. But there is more to say to that. Already in this very well-known review article by Muga and Levens in 2000, they observed that several theoretical treatments converge to essentially the same arrival time distribution at asymptotic distances and times from the particle source and intervening scatterers. So this means that if you go and place the detector somewhat far away from where you prepared the initial particle in, more or less, a lot of approaches will look one and the same. This has also not been really quantified, and Detlef and I tried to quantify that, as I will show you in a couple of slides down the line. And this also suggested that, okay, so we need to get closer, so go near field to see meaningful differences between different arrival time candidates. But near field is really impractical for experiments, because if you place the detector very close to the place where you created the initial wave function, the particle will be practically detected instantaneously. And there is no way to resolve these arrival time statistics unless you have very cutting edge time resolution equipment. This backwall experiment, as we call it, and I will describe, so this is the main part of this talk, really fulfills this gap. So it allows us to measure at a distance away but still manages to induce really significant differences between, I would say, almost all arrival time candidates available so far. All right. Before I discuss these candidates, I should talk about two attitudes or two approaches in this arrival time program. One is the ideal approach in which arrival time distributions are predicted in a measurement independent way. So formulas are given just as functions of the initial wave function, as functions of the surface of the detector, and that's it. Whereas in the non-ideal approach, the measurement is taken seriously. There is a model of the detector typically, sufficiently easy and analyzable model. And then the arrival times are, so the arrival time distribution is then calculated based on the model. Well, of course, the second option sounds more correct, and really that is how one should do it. But the idealists normally have a sort of argument, which is as follows. You know, they say, look, experiments like double slit, experiments like Stern-Gerlach, any scattering experiment of the day has barely ever been analyzed by taking the detector any more seriously than basically not being there, right? So why should I suddenly take the detector so seriously to predict arrival times? That raises more questions than answers. So this is the kind of argument you would hear from an ideal guy. Whereas the non-ideal guy would say, no, in quantum mechanics, at the end of the day, the detector is crucial because measurement results are contextual. It depends very much on the entire setting, on what you are calling as your detector, how you're detecting, and so on. And to give you an example, this which way measurement is, of course, the best example here. Because if you don't consider the fact that somebody is looking at you as you go through the slits, you will not predict the disappearance of the interference pattern. So both positions are compelling, I would say persuasive, but at the end of the day, each of them comes up with a formula, and that's all that you can test against observations. So with that, so this is a little bit of the technical zone. And if there are some people who wouldn't like to follow, I would just request you to bear with me. So one of the early ideas to get an arrival time observable, that's an operator acting on the one particle Hilbert space. I mean, this is the closest you can get to the program of quantum mechanics described in textbooks. This goes back to work by Aharonov and Bohm in 1961, where they considered, to begin with, and very simply, the classical formula for the arrival time of a point particle moving on a line. And then they promoted this classical formula into, hopefully a respectable operator. I say respectable because this has a lot of problems and I will not have the time to go into details. But the expression in the box is the so-called Aharonov-Bohm arrival time operator. You can see this symmetrization of the Z and P operators because they don't commute. So this Z over P goes on to this. I mean, this operator will also come out if you follow, for example, the Weil quantization scheme, or also there are others. And this can be seen as an instance of the correspondence principle, where classical expressions are promoted to quantum observables. An early thing to be appreciated about this operator was that it commutes with the free particles Hamiltonian, just as you would like, right? So here is the commutation relation. And this immediately begs the question, do you have a time energy uncertainty principle? So in the early days, a lot of the interest around this operator was driven by the possibility of a time energy uncertainty relation. I'm sorry to say that relation cannot hold for all wave functions based on this operator. And I would really encourage you to look at this recent paper that I wrote with Marcus, who is also here. And this gives you a very pedagogical and historical account of the developments starting from 1961 until the present in this class of proposals. All right, so by the way, I should mention that that operator is not even self-adjoint, so it wouldn't be observable in the traditional sense of the Ark and von Neumann, but it managed to define an arrival time distribution in the sense of POVMs. I'll talk more about POVMs later. And the final expression that you get from this operator roughly looks like this. So it's the sum of two inner products squared, and then you can give a formula for the inner products. And yeah, and then, as I said, there are many problems with it. In particular, from a physical point of view, it predicts negative arrival times, which leads to vanishing of expectation values for certain real wave functions, and the list goes on. Let me move on to some possible generalizations of this operator for non-free motion, because in experiments, there will be non-zero potentials around the particle. So we are not getting much further if we just have a proposal for a free particle. And as you can see, the starting point in this business is the classical arrival time expression. And seldom do you have an explicit formula for the classical arrival time expression in Newtonian mechanics. And even if you have, it's going to be, God knows how nonlinear. So good luck to people who want to put hats on it, right? And so there is not much you could do, but there are good ideas by some authors. And so here is one distribution, which is called the standard distribution. They don't start from the classical expression, but they simply look at this integral, and they see this p squared by 2 is the kind of the evolution that you get in momentum space for a free particle. So they change it to evolution by a generic Hamiltonian. Well, this is a little dangerous, because then this new distribution is not guaranteed to be even normalizable for all potentials, but usually it is. And then it actually fails to be a POVM. Then there are ideas by other authors where they look at potentials which vanish sufficiently fast as you go away. So where you can define these scattering or Mueller operators, and then there are such ideas. And there are some more. But this is a very popular direction of investigation. Then there are some semi-classical approaches which you can find in the experimental literature. One is based on the idea that you can just take the classical arrival time formula, and which is correctly viewed as a function of the initial position and momentum of the particle, and just integrate it, putting it in a delta function kernel against the Wigner function, the Wigner quasi-probability distribution defined by the initial wave function. Of course, this is not a positive definite quantity, so it's not a probability distribution, but for most practical purposes, it gives you reasonable results, and you could compare with experiments. Then there is another idea where, one would say, by the way, it's not due to Heisenberg. So I didn't mean to say that the idea is due to Heisenberg, but it's extremely close to what he was saying in his 1987 Chicago lectures. And this is also, I would say, really the bread and butter of momentum spectroscopy. Namely, the idea is to think that the particle propagates in a straight line, and the initial momentum is randomly distributed according to the quantum mechanical momentum distribution. And if you do a little math around that, you would get the second expression in the box. There are also ideas in which people would claim that the distribution of arrival times, even in a single particle experiment, let me allow you to take note of that. Even in a single particle experiment, people would say corresponds to the temperature of the particle. So they would assume that there is a Maxwellian distribution of velocities at time zero, which features as an arrival time distribution via Newtonian propagation, even for single particle experiments. And that's quite telling. Next, I want to go to the Bohmian way of doing arrival times. And here I'm mostly going to describe the approach by Levens and also ideas by Der, Goldstein, and Zangi in the scattering papers. This is also an ideal approach in which the detector is not going to be taken seriously. I also have just a one-slide introduction to Bohmian mechanics because it doesn't need more. It's a theory where particles are moving on trajectories, and all you need at the end of the day is an equation of motion, which is explicitly given here. It's also called pilot wave theory because the velocity of the particle is given by the quantum mechanical wave function evolving according to Schrödinger's equation. So the wave function guides the particle along deterministic trajectories that satisfy this equation of motion. Now, different initial conditions correspond to different realizations of particle positions across different runs of the experiment. And there is a theorem from the Goldstein and Zangi, which says the statistical distribution of initial positions in a sequence of experimental runs is chi-square distributed. And the picture on the left is one of my favorite pictures and produced in our group by a former colleague, Leo Kellers. It's also the picture which Sandro already showed. But the difference here is here the double slit barriers are explicitly taken into account in the evolution of Schrödinger equation. And you can see the picture is extremely self-explanatory. All of you have seen it many times. I'll just move on. And this is a slide again I like. No, this is not the slide, the next one. Sorry, I'm getting ahead of myself. So this slide is just how you would define arrival times in Bohmian mechanics. You would take the trajectory and you would look for the time at which it strikes the surface of the detector. I should be careful here. I'm looking at the first arrival time on a given surface. In the literature, this sometimes is presented in the form of a truncated flux, but this is an easier description. And then if you look at all possible initial positions from a chi-square distribution, you immediately define a well-defined arrival time distribution. One thing I should emphasize, there is no reliance whatsoever on classical mechanics here. And of course, no talk of observables either, because Bohmian mechanics is a deterministic theory of particles. There are no Hilbert space observables in this theory. By the way, this distribution, although easy to write down, is extremely difficult to calculate numerically. But I'll give you one example, and this is a slide I really like. The picture on the right is data that I showed you on the earlier on the second or third slide. And the picture on the left is a picture from the thesis of Leo, the guy who made the double slit pictures. And basically, this is a rendering of arrival times of individual trajectories plotted across the, so it's plotted as a function of one of the coordinates of the screen on the horizontal axis. I'm not claiming that the picture on the left and right are basically equal or they fit each other. But you know, I tend to take this not as a mere coincidence. I really highly recommend looking at this thesis of Leo. It's available on our website. It's an extremely beautiful piece of work done by any master student. Okay. As I was just saying, the Bohmian arrival time distribution is very difficult to compute in general, but under special circumstances, when all trajectories exit this surface of arrival at most once, this distribution reduces to the so-called quantum flux distribution, and that distribution can be explicitly written down as a simple, nice formula as a surface integral over the probability current of quantum mechanics. Okay. Now, this distribution, this quantum flux distribution, has been independently arrived at by other authors, mostly in one dimension and for freely moving particles. But if you take this formula as a complete formula on its own, then you are in trouble because there are wave functions for which the right and this formula is not positive anymore. And those wave functions have become of great interest to the literature in the recent times. And they go under this term called backflow effect. I will tell something more about that later. But if the way I see it, I like to see it as a special case of the Bohmian arrival time distribution, in which case I always know which wave functions to use it for and which wave functions not to use it for. Anyways, I should also add that the quantum flux distribution is not a POVM. So this doesn't define a quantum observable in the traditional sense. This is proven by Detlef and former students in a 2013 PRL. a nice paper, you can take a look at it. And I'll say more about quantum flux as I go on. These are some papers of other authors who arrived at it independently, as I was just mentioning. I want to talk about two non-ideal candidate arrival time distributions. The first one I particularly like is due to Werner and Tumulka. I think Werner just suggested it in one of his papers, and Roderick Tumulka developed it extensively. The idea here is to stick with the Schrödinger equation, no trajectories, no operators at the moment, but let the wave function evolve with a certain boundary condition on the surface of the detector. So this nu here is a phenomenological parameter that models features of the detector. It has dimensions of 1 over length, if I'm not mistaken. And this boundary condition, of course, makes the evolution non-unitary. But what it does is it guarantees that this formula, this J dot ds, is always positive definite. So if you take J dot ds with the usual Schrödinger evolution, there is no reason for it not to become negative for a certain wave function. But with this absorbing boundary condition, ABC, you are guaranteed to make that positive for every wave function. And so at the end of the day, you can use the quantum flux formula with this absorbing boundary condition. That would be the ABC prediction. Then there is an approach which is very similar to ABC in the end. It's not exactly a boundary condition, but it's not far from it. And I'm not getting into details. It's coming from people who developed event-enhanced quantum theory, or EEQT. That would be a story in itself, so I'm skipping it, I'm sorry. And then there are, of course, approaches from path integrals with different boundary conditions, and I will show results from those approaches as well. And then there are a few more that I wouldn't have time to discuss. There is the proposal that the arrival time distribution, these are also non-ideal, meaning these were derived by taking the detector seriously, or some model of the detector seriously. So here there is a suggestion that the square of the wave function, the thing that gives you position probabilities via Born rule, is the arrival time distribution. So the time argument of the wave function after squaring it, so the arrival time distribution is proportional to that. I'm not going to defend this position, but I just wanted to mention the main point here. And there is an approach by approach which I call the restricted propagator, also from path integral community. Then there are ideas from few chemists also based on kinetic energy density, and the list is essentially endless. I didn't even mention all of them. All right, so the interesting part now. So now I want to call you back, those who lost me in the technical interlude, because now we are getting to more delicious material. So here I have two setups. They are very schematic. And this is exactly how discussions with experimentalists has taken place. So this is how the experiment will unfold in practice whenever it is done. The idea here is to do single ion experiments with ion traps like Paul traps, Penning traps, what have you. And the idea is to take a single ion and, I'll talk about the experimental details later, but the main idea, and this is Detlef and my backwall experiment, and we have worked very hard on this, and I hope you appreciate these results at the end that I will show you. The idea is take the particle, trap it in a harmonic potential, which is what experimentalists do to prepare the particle in a ground state. Don't worry about the ground state. It's, as I said, all you need is a definite quantum state to calculate predictions, and the same state should be reasonably preparable in experiments. And then if you suddenly switch off the trap after cooling the particle to the ground state, it just evolves according to Schrödinger equation. And then you will see clicks on a distant detector due to the spreading of the wave function. Now on the left, you have a situation where the trap is switched off completely and the particle is, let's say, moving freely except for the detector that is sticking around. And in this situation, you will fail to distinguish most arrival time predictions that I just described. And I will give you concrete proof of this claim in the next slide. So experiments will be inconclusive if you just let the particle completely free. And this is exactly what Muga and Levens observed in their review article, although they did not support it by any concrete computations. Whereas a better experiment is this backwall experiment in which you don't switch off the harmonic trap completely, but only half of it. Now that might sound strange. How can I switch off half of the harmonic trap? But if you think about it in the experiment, this harmonic potential is realized by placing two Gaussian barriers next to each other. So what I'm saying is remove one of the Gaussian barriers. So in that case, the particle propagates in the direction of the detector, but always in the presence of a potential barrier to its left, as shown in the right panel. And this experiment is particularly nice because it's analytically tractable. It's not the evolution, I'm not saying it's easy, but the evolution is not very far from free evolution. And for this setting, you can calculate almost all of the proposals that I discussed and also some that I didn't discuss, and you can compare against experiment. And the good news is the right-hand side, the backwall setup induces extremely precise and measurable distinctions between a lot of these candidates that you can detect. And this, please take note, even in the far field. So you don't have to place the detector very close to the initial wave function to see differences, as you would need to if you are in the left setup. But in the right setup, you can go as far as you like, and the particle will take its own sweet time to get detected, and you will still see significant differences between different approaches. Okay, so with that, so here is a picture of a Paul trap. Because I was expecting it to be mostly theories, so I thought I will show you some experimental pictures. So this schematics that I showed you in this slide is more or less taking place in this small, teeny tiny region here. So the particle is moving in a vacuum region. So it's a very small region. I'll give you numbers as to what distances and time scales are involved in the next slide. Single ions, as I was saying, laser-cooled single ions, typically calcium, thorium, rubidium. There are a few options available. The initial ground state is really, for all practical purposes, the Gaussian harmonic ground state, which has a width of about few tens of nanometers. And the distance at which you can place the detector, of course, depends on how long you can, on what distances you can maintain coherence of the wave packet and so on. Typically, a few 100 millimeters is possible, 1 centimeter, and so on. And one thing I want to mention here is that if you take, let's say, just for example, you take the distance to the detector to be 0.3 millimeter, just for example, then the arrival times expected are in the range of about in the range of 1 to 20, 30 milliseconds. And that's quite nice because the detector, the time resolutions that you expect in these experiments are a few nanoseconds, and this time scale is a couple of orders of magnitude above that. So the resolution will not be a bottleneck. Then the detection method, well, there are two ideas that you can implement with ion traps. Maybe there are more if some of you would like to suggest in the discussion section. One is to place a very thin laser curtain, which induces fluorescence as the ion passes through. Or you could also, this second option is a bit tricky, but the idea is to place a scintillation screen made up of electron multipliers, a microchannel plate, and so on. So this is just to give you some experimental flavor. Unfortunately, I don't have any experimental data to report today, except for the double slit data that I already showed you. And here is the first picture. This is the picture for without backwall. So you prepare the particle in the ground state and let it completely free. And these are the different arrival time predictions from various different proposals. Let me spend a minute on this picture. If you are wondering why the green curve has gone off the figure here, I want to remind you of this normalization from the beginning slide. Remember, I told you every approach not only gives you an arrival time distribution, but it also predicts whenever possible, the non-detection probability. So these distributions are normalized in such a way that the total integral under any of these curves gives you the probability of detection, meaning it's proportional to the fraction of experiments in which you observe the particle at the end of the day. So in a freely moving case, the wave packet is moving bidirectionally, right? It's symmetrically spreading to the left and the right. You would expect that half the times you will not detect the particle because it's kind of going on the other side. And all these blue, red, and black curves more or less respect that intuition of ours. Whereas these green curves, by construction, always predict 100% detection for any wave function. And that's why they are normalized to 1 and they're off the figure. But what's important in this picture is this red curve. As you can see, most approaches basically coincide on top of each other on this red curve. And that's what I was already warning you about, that if you were to do this, obvious arrival time experiment, release the particle completely free, there's no way to conclude which among these is correct or more correct, if I may say. Are there any questions at this point? I have spoken for some time. If none, I would show you the next picture. Okay, seems like there is none. All right, so this is the back wall results. I have put a few curves because it was not possible to put all curves in the same picture. There are about, as I said, 15 to 20 approaches. This black curve here is what's interesting, because previously in the red, so a lot of the approaches which appeared on the red curve before are now on the black curve, but only a few of them, not all of them. The remaining have degenerated into their own different curves. And that's the beautiful thing about the back wall experiment. It's actually, the specifications are same for the previous figure and this figure. One thing I want to highlight is this pi AB and this semi-classical and Wigner function. This AB stands for putting hats on classical expressions. That couldn't be distinguished before from approaches like the Bohmian one, or from the one where people would claim that this is a temperature measurement, reflecting temperature of the particle, whatever that means. Those can now be clearly distinguished. You cannot fit these distributions to those coming from, let's say the Bohmian one or the chi-square one. Those are clearly distinguishable now. One thing I should mention, that all these curves are based on exact analytical expressions. So no approximations have been made in producing either this figure or this one. So if any of you are wondering if there is a chance to see much difference, if I do better analysis, I wouldn't say there is a lot of chance for that. All right, so yeah, by the way, this is the picture that you get from this absorbing boundary condition proposal, where you had this boundary condition on the detector surface. So this approach without the back wall was given by this dashed curve. You can see that it's kind of close to the red curve. I chose the free parameter of this distribution to come as close as I could get it to the red curve, so that we can check, whether this can be distinguished or not. But once you have the back wall, actually it becomes very difficult to plot this distribution for the real experimental parameters, because the distribution develops these oscillations on very small time scales, which makes it numerically a little hard. But again, this is based on an exact solution of the Schrödinger equation with the absorbing boundary condition and with the back wall. So this also gives you very distinct signatures, very interesting and distinct signatures for the experiments. The good thing is all these approaches that I described have their own characteristic power law tails, whether it's with the backhaul or without the backhaul. And those are, as far as I can tell, very robust to differences to the shape of the backhaul, the potential, the distance at which you measure, and so on. And there are a few of them. Some of them I have not written down because some candidates have two tails actually. They develop a real power law at much later times, which will not be experimentally accessible. But the point is they all have different power law tails, and you can definitely see that on a log-log plot of the arrival time curves. Could you tell me, Paula, how much time I have left? I'm almost at the end, but I wanted to know.
Yeah, you can, I think, go on for some minutes at least.
Yeah, I'll just wind up in maybe 5 minutes.
Yeah, 5 minutes, fine.
Then I would be okay for questions. I want to go back to this slide to remind you about the quantum flux distribution. I introduced it as a special case of the Bohmian arrival time distribution whenever the trajectories cross the detector at most once. There are very beautiful results by Durr, Goldstein, Zangi, Martin Daumer, Stefan Teufel, Peter Pickel, all our group members, on scattering theory. There's a lot of good things I have in mind about those papers, but one thing I want to highlight, which is not appreciated in the regular scattering literature, is that the reason standard scattering theory works to a large extent is based on the properties of the probability current in the far field. And these studies have shown that this current, which is just governed by how the wave function evolves according to Schrödinger equation, it so evolves that the current becomes manifestly outward directed. So it becomes practically radial at large distances. And these results even hold for short and long range potentials. That's quite striking. So this expression for the arrival time distribution, if you have if a detector sufficiently distant, a sufficiently distant detector, these results from scattering would imply that pi QF is always well defined, meaning it's a positive quantity. And indirectly, it's telling you, the Bohmian distribution and it are the same, okay? So it has been of much interest in the literature to really figure out examples where this fails. And there are many papers on this as of today. If you Google the word backflow effect, the quantum backflow effect, you will find many papers. There are works by Michael Berry on this. He tried to come up with examples of wave functions where the current becomes negative. Arseny Gusev is one author that comes to my mind, Jonathan Halliwell, and so on. But what's funny, or maybe unfortunate, I would say, is that in a lot of these examples, there are only fleeting moments of time at which you can make this quantity negative, and mostly in one dimension. So just forget the three-dimensional character of this for most practical purposes. So the Schrödinger equation is so directing the wave function that for all practical purposes, this is a well-defined quantity. It's extremely difficult to render this quantity negative. And the literature is witness to that. But, this is out of serendipity, the setup that I worked with Detlef for my master thesis. And at that time, I don't think there was so much interest in the backflow effect, turned out to be one in which this probability current becomes manifestly negative at any distance along the propagation of the wave. So no matter how far you go, and it is negative at any given time. So it's an extremely stable backflow situation. And the second important thing to say here is that it's literally, how should I put it? I mean, on the one hand, I want to say that it's really experimentally doable. And I think it's literally the setup to test arrival times, as I will try to convince you. anyways, so before I get ahead of myself, the experiment I have in mind is exactly the same as before. It is a back wall experiment, meaning there is a back wall, and initially the particle was prepared in some region, like a box, and then it was prepared in the ground state and set free. Here I have drawn a waveguide. Although the wave, I never emphasized on it, the waveguide was always available before. So, I mean, in this back wall experiment also, there was a waveguide. You know, the Paul trap creates a potential to confine the particle cylindrically, but I didn't need to emphasize it before. But now I want to emphasize it because that plays an extremely important role in inducing this backflow. But the backflow doesn't happen for a particle governed by Schrödinger's equation, but for a particle governed by any of the spin-half equations of quantum mechanics, namely Pauli or Dirac. And so I'm now talking about wave functions which are spinors, which are, you know, multi-component objects. And here I have in mind single electron for the sake of discussion, prepared in a spin polarized wave function as I've written down here. Spin polarized just means that the spatial dependence of the wave function and this so-called spin dependence are factorized. So the position dependence is completely sitting here. And here we don't have one wave function, but a family of wave function described by two free parameters, which are, you know, angles, spin angles as they're called, spin projection angles. And in experiments, you can, I mean, it's not easy, but you can in principle tune these parameters in this range and prepare different wave functions. This last expression here is important. I'm imagining a surface at a certain distance L, which is where I want to look at arrival times. And here, the probability current component, so the component of the current perpendicular to the surface is Jz, as I have set up the axis here. And it roughly has this form. I mean, this form is exact once you know the wave function, but I want to highlight that this second term, which is sitting here, is the reason why it becomes negative. It's well known by now that the probability current for particles with spin is quite different from the probability current that you get from Schrödinger's equation. So that's partly the reason for seeing some new behavior in this circumstance. And the other part is, of course, the waveguide, which is new in this setup. Well, this rho 0, which is sitting in the denominator, is the diameter of the waveguide. And I want you to notice that this rho 0 is a free parameter of the experiment, meaning you can tune the diameter of the waveguide as you like. And you can make this quantity manifestly negative as much as you like in some sense. Another thing to notice is that nothing on the right-hand side of this inequality depends on the place at which you are looking at the current and the time at which you're looking at the current. So this is why I claim that this is a robust backflow situation. And apart from which approach you like, you know, if you have a favorite approach or not, this alone is a very good reason to measure arrival times in this setup. Because whatever comes out, it should shed new light on this long-standing controversy. And so far I said nothing about Bohmian mechanics. This is just Schrödinger evolution or Pauli-Dirac evolution. So this is all the wave function tells us. But for computing potential candidate arrival times in this setup, most approaches that I showed you wouldn't work because they have not been generalized so far for spinor valued wave functions. So it's inappropriate to just extend them by hand and say, look, this is how they look like. But the Bohmian approach, as I said, was never designed to study arrival times. It was always built as a quantum theory that makes sense wherever and whenever you want to apply it. So spin was always on the cards from the very beginning. I want to show you a Bohmian trajectory for the wave function when alpha.
Sorry, can I ask one question was asked in between? When you go back one slide,
Yeah,
there was the phi below, and the question was, what is the phi?
Oh, I'm sorry. So I was too quick. This phi is actually, I'm using cylindrical coordinates. So rho, phi, and z are these three coordinates of the vector x. The position coordinate of the particle is expressed in cylindrical coordinates. That's what I want to say.
Okay, thanks.
Thank you. I want to show you one trajectory for the wave function when this alpha is 0. So this is, the famous spin-up wave function. And you see that the trajectories are, simple spirals. This is just one trajectory and others look more or less like this. And for alpha equals 0, you can see this sine alpha makes this term 0. So there is no backflow if you set alpha to 0 according to the expression below. I mean, there is no obvious backflow at the moment. So in this case, you should not expect deviations of the Bohmian trajectory arrival time statistics from the quantum flux statistics. Okay? But if you make alpha pi half, which is where sine alpha is 1, so that is the maximum contribution sine alpha can make as in the second term, you get really the best backflow you can get in this setup. And that corresponds to a wave function, which is an equal superposition of 1, 0, and 0, 1. So it's an equal superposition of spin up and down, as one would say. And these are some typical Bohmian trajectories. You can see they're very different from what you get in the spin up case. Now, over the last years, along with Detlef and Marcus in particular, we have looked at this setup in great detail and many variations of this setup where you can play with the waveguide, play with the potentials. These general features of the trajectories are extremely robust. They just don't change if you change the potential, what have you. So that also gives some, what should I say, confidence that, this is not very sensitive to small changes and so on. And finally, I want to show you the picture that some of you really like, is the results that we get if you just follow the trajectories and look at the statistics of arrival times. The blue curve here on the left, the blue curve is the one that you get from the spin up wave function, the one where alpha was 0 and the trajectories were spirals. You can see that it is superimposed on a black curve, which is this quantum flux prediction, the expression J dot ds, which I told you has also been arrived at from other approaches before. And you can see that blue and black are exactly on top of each other, as they should be, because there is no backflow in this for this wave function. But as soon as you start tuning alpha different from 0, that is, as soon as you move closer to pi half, meaning closer to the case depicted here, the tail of the arrival time distribution starts shrinking compared to the blue curve. And the moment you are at alpha equals pi half, literally in theory, the tail shrinks to 0. And after that, the distribution is completely vanished. Of course, for a long time, we thought this was just numerical artifact. It need not go to 0 strictly. But we have this paper that came up within a year from observing this, along with Marcus Nert and Detlef. I mean, this is one of my very favorite papers, and I really request you to go through this. It has extremely nice material on how to analyze Bohmian dynamics with spin, how to talk about arrival times. And if you're a dynamical systems person, you would really enjoy this. And last but not the least, you can also get nice examples to set exercises for differential equation courses. Anyway, on a serious note, the shrinking of the tail of this distribution as a function of alpha. So different alpha corresponds to different wave functions. So you prepare the particle in different spin polarized states. If alpha is 0, insofar as the analysis under these pictures is correct, you should expect the tail to show up completely in agreement with quantum flux. If you prepare the particle in this spin up down or alpha equals pi half wave function, I mean, in theory, you will not see a strict tail, but in practice, maybe you will see a little bit of a jitter there. And here what I've also plotted is this semi-classical prediction, which I was telling you is the bread and butter of momentum spectroscopy. You can clearly see the difference from that, right? That is completely based on classical trajectories and momenta distributed according to quantum mechanics. And finally, the picture on the right is showing you the mean of these distributions as a function of alpha. And the shrinking of the tail of the distribution just pushes the expected arrival time to smaller values. And you can see that it reaches its minimum value at alpha equals pi half, and then again goes up. So this is more or less, I just wanted to put as a flashcard before you. There is much more to say about this, and this can go on for hours, and that's not the purpose of my talk. With this, I want to thank you for your attention. Thank you so much for coming and spending your time. And last, I wanted to say this in German, but I will not, making a laughing stock of myself. But this goes back to actually Einstein's paper when he predicted the bending of light for the first time. And there he says, go out and measure to the astronomers of the day. And to the experimentalists present among us, I'll just say the same, go out and measure. With that, I rest my case and thank you so much for your attention.
Thank you, Siddhant. That was very interesting talk. I see some faces now. So yeah, please. Yeah, whoever wants to ask a question. Okay. Sarita Vildasade and Michael Kiesling.
Yes, we are watching together.
Extremely happy to see you. Thanks for coming.
Yeah, that's why you don't see me logged in. So I'm
I wondered.
So thank you, Siddhant, for a great talk. I have two questions quickly.
Yes.
One is about the when you talked about this, you put this harmonic potential and then you remove half of it to get your back wall effect. Isn't that more or less similar to having a boundary condition behind the particle?
If you have a hard wall in mind, right? Like an infinite potential.
Yeah, I mean, so it's sort of, it has that kind of flavor. I was wondering if you could also study that situation with a boundary condition there.
Oh yeah, oh, so sorry, I was too quick. Actually, this second figure is for the hard back wall, actually. So these figures are for, I'm so sorry, I should have told you that I didn't mention the potential I had taken for the back wall for this figure. It is the hard back wall. So it's exactly what you are saying, the back wall, which is—
Oh, I see. Okay.
I've also looked at smooth walls, but that just gets too involved. But the important message is these power laws don't change much more meaningfully than what they are here.
Okay, that's great. And if I may ask another question, that's so it's my understanding, and you can correct me if I'm wrong, that the absorbing boundary condition proposal will not have this backflow problem.
Yeah. Yes.
Is that correct?
Yes, that's correct. But what's interesting is in the absorbing boundary condition, you will also see spin-dependent arrival time statistics because the backflow is a spin-dependent phenomenon coming from the wave function.
Yeah, I meant the absorbing boundary condition, say for Dirac equation.
Oh, yeah, that's of course very difficult to solve, but sure. I mean, at the end of the day, it will predict. Maybe not the same because these are extremely exotic statistics, as Detlef like to call them. But it will definitely predict something which is alpha dependent.
I see, but you don't have any figures to show for that.
I don't think I will ever be able to calculate that. That's extremely hard as a differential equation. Sorry.
Okay.
Thanks.
So let's come to the next question. Lorenzo Marcone.
Hi, Siddhant. Great talk. I really appreciate it.
Thank you.
So I have a question and a comment. The question is, do you expect that if you put in the situation you were showing, in which you have the back wall and the particle propagating, what if you put a potential wall in between?
Like a tunneling situation?
Yeah, not tunneling. Yeah, like a tunneling situation in which you have like reflections back and forth of the particle before it reaches the detector. So you would have interference. Would that be an interesting situation?
That's an interesting situation. And in fact, that's a research program that my colleague Marcus is embarking on. So maybe in the next offerings, he will have more to say about it. But as far as arrival time predictions go, it's just the computation which becomes very different. But my program here is to do as minimal as possible on the math front, that you can distinguish these competing predictions. And a barrier is extremely difficult because you don't even get closed form expressions for the solution of Schrödinger's equation, except in the delta function barrier case.
Great. Okay, thank you.
The comment, you had a comment?
Yeah, the comment. Yeah, one thing that I would underline on this, I mean, it seems weird that we don't have as you were saying, an accepted time of arrival observable. And I would trace that to a very fundamental reason. And the reason being that when you look at quantum mechanics, the probabilities are always calculated through the Born rule. And what people tend to forget is that the Born rule is a conditioned probability on time. So it's the probability that you obtain some result given of a measurement given that the time is t. So you're always, in whatever picture you're working, Schrödinger picture, Heisenberg, it's always a conditional probability. So of course you run into problems. I mean, it's not impossible from a conditional probability to get the probability you're conditioning on, but it becomes very, very complicated, like you were saying. So it's just a comment on the fundamental reason why it becomes very difficult to obtain a time of arrival distribution because of the conditioning nature of Born's rule probabilities.
I can say one sentence more on that. Actually, I wanted to put a slide referring to von Neumann's measurement model to highlight that the quantum mechanical framework of textbook is more like, at a given instant of time, what's the position of the particle? At a given instant of time, when you choose to measure something, what's the momentum of the particle? Yep. You as an experimentalist choose the time at which you look.
Yep, exactly.
But here, the time at which the detection takes place is the object of interest. That's the random quantity whose distribution we want. And the best, I mean, this is with words, but the best mathematical manifestation of this difference is in the von Neumann measurement model. For those who know it, it's in the last section of his textbook where, you know, he takes pointer states. You know, if those who don't know, don't worry, but he takes these pointer states and he couples it to the particle state. And then there is an interaction Hamiltonian, which has a delta function. So there's an instantaneous interaction. It's a model. So it's a bit sketchy there, but it has a delta function which fires at the time at which you measure.
Yep.
And that is taken by many as basically the quintessence of textbook quantum mechanical measurement formalism. Yeah. And that time has to be put into the Hamiltonian at which you are measuring. And there's nothing like that in the arrival time context.
I agree, totally. It's a different way of saying the same thing I was saying.
Yes. Thank you.
Okay, so there's a question by Ward.
Okay, hi. Thanks for the talk.
Thanks.
So I had a question about these non-ideal proposals. Okay, so for these proposals, it's important how you do the actual measurement, if I understood this right. Mm-hmm. But the question is, so is a prescription provided of how the measurement should be done? Because it doesn't seem that you have taken that into account in
well, well, you know these things.
Or what I mean is, like, you have all these plots, right, producing different arrival time distributions.
Right.
But it could be that you still couldn't distinguish them because maybe different people propose different ways of how these measurements should be done. I don't know.
There are two things to say to that. One thing is, at the end of the day, the non-ideal guy also gives you a formula. The formula might depend on one or more free parameters. That's okay. You can scan the parameter space and see what are the best conditions. At the end, there is a formula and that can be tested. The second thing to say is, there is this attitude from the non-ideal side largely that, you know, everything is correct. You just have to find the right way to measure it. And that is a reflection of this Copenhagen idea that all observables are equally there. You just need the right experiment to measure it. People have already criticized it. The way I would put it is, if you're a non-ideal guy, listen to the way it's going to be measured. So discuss it from the beginning. Do you agree on it? If you are okay with it, then put your bet on the program. And if you don't agree on it, well, then look for the way to measure it. Otherwise, it will never be measured. It would be only in the published literature. That's the way I tend to think about that thing. I mean, there is only a few, I mean, what will you do in the experiments? There is only a screen you can put. What more can you do? Things have not moved much from 1926.
Okay, thanks.
Thank you.
There's one further question by Christos Eftimiopoulos.
Thank you. Well, actually, it's a small comment and question on what Ward asked before, because the actual procedure counts a lot in this kind of, I recall some years ago, we tried to write a couple of papers on arrival times. And I figured out that the community working on the experimental side on this define some procedures. So for example, to measure time, you need a start event and an end event, let's say. The end event is typically the detection of the particle, let's say the click. This we all understand.
Yeah.
But the starting event is tricky. So essentially, it means that you have to have a way to measure at what moment exactly your state was prepared. So let's say you can assume that you have a gun of particles, like those particles that you mentioned before, those, let's say, spinors, essentially.
Mm-hmm.
But then you need a device that produces them one by one, by the way. So
sorry, I didn't want to interject you, but maybe I was not clear, because in our case, we actually always trap the particle in a potential and then switch off the barriers suddenly. And that's taken as time zero. So it's not a gun which is shooting particles one after the other. It's a single ion experiment.
Exactly.
Every time.
So it's the same. I mean, essentially, you need a process that will switch the potential off, let's say, sort of speaking. I mean, you need to have a way to change, essentially, the potential at a certain time, that this is going to be called the time zero. But this has to be measured, because, of course, you don't count on just a classical switch that you will turn the potential on and off by just pressing it with your hand. I mean, you need probably another particle. People have assumed this to be possible to do, by example, using laser-induced cold emission. I mean, just to mention some process. And that process is quantum itself. So, for example, in laser-induced cold emission, you involve a tunneling effect. So essentially, you change the potential by a bit, so that tunneling can make your particle go out. Okay, but then these events have their own probabilities, and eventually, what is always claimed. I mean, just to come to a comment that was asked, that was made before. Eventually, all those things that are measured, sort of speaking, let's say the starting and the refer in some sense to a classical observable that then is interpreted as a time measurement. I mean, just to use very simple, let's say, assume it's a classical chronometer. Okay, you have an analog chronometer. Okay. So what you will really measure is the position of the pointer. Mm-hmm. Okay, so in the end, what we call measurement somehow has to be transformed into a process in which the final quantity that we claimed has been measured is an observable by itself. And this is interpreted in time afterwards. So what I'm trying to say here is that a correct analysis of these, sort of speaking, experiments, because we can make, of course, we can make many theoretical predictions based on fluxes, Bohmian trajectories, and so on and so forth. But eventually, for experimental physicists to accept and even to go and measure, as has been the proposal, you would have to figure out a complete measuring process by which you explain why the observables included in the actual measurement should be interpreted as time measurements themselves.
Well, so I see a point. I mean, such a fundamental analysis, of course, is out of my scope at the moment. But what I gather is you are saying, even if you're, I mean, I take this as the main point, that the switching off itself has some uncertainty. So it's not necessary that nothing is instantaneous. So there is a small amount of, in some runs of the experiment, you release the particle came out a little earlier, or maybe it came out a little later. I guess that's the concern here. And then you are saying that should be taken into account to analyze arrival times, right? In the analysis of the arrival times. Well, one thing, I don't know if it helps you or if you prefer, if you would like it, is that, I told here that all these approaches which take a single, so these theoretical approaches don't take into account this jitter at the time zero, right? And these models come, let me track back. So all these approaches have a given time zero. And you're saying in experiments, that's a random variable in itself. But what's nice is here you have power laws. And typically these delays that you get or uncertainties of the starting time can be expressed as convolutions of, let's say, ideal distribution with some response function. I mean, you were talking about this laser detection approach. They also came up with the convolution of a certain response function with the quantum flux at one point, I remember. Convolutions and these response functions are typically exponentially decaying. And if you convolve something with an exponential function, the power laws are strongly preserved. That's just, so I think that gives me some hope. I should also add that I have also looked at situation where the barrier, this harmonic front wall, is not switched off suddenly, but exponentially, like, with the e to the minus lambda t. I didn't see much of a change, of course, in the results, but this is as much as a pragmatic theorist can do. Yeah, so that would be my response to you.
Okay, so I think we should go on. There are two more questions by Aurélien Dressé.
Okay, so thank you for this great talk. I wanted to point the analogy with optics. In quantum optics, a lot of experiment has been done on correlation, and it's a kind of finger on the previous comment by Christos, because it's if you want to measure time in quantum optics, you can make correlation between, for example, two avalanche photodiodes. You can you can measure statistics in time, and you can make anti-branching curve, for example, with photons to measure single photon source emissions. And of course, the photon is a bit different from the atoms or the non-relativistic theory that you are considering here. But I believe that if you go to textbooks on quantum optics, like the book of Emil Wolf, where you find a lot of this discussion about statistics of photons arrival and things like that, it could be interesting to see if you cannot get some clue, some interesting physics to solve your problem.
Yeah, so those are interesting research programs we would try to step into slowly.
Okay, so there's one more question, and then I think we should open it up to the general discussion. So Anirudh Chandrasekaran.
Thank you. Thanks, Siddhant. It was a very nice talk. This is related to Christos' question. Perhaps Siddhant or Christos could clarify this for me. I'm a condensed matter theorist, and I can attest to the fact that RPES is a very, really produces band structures quite well in many cases. I just want to ask, if these limitations that Christos highlighted, either with respect to t equal to 0 or with respect to analysis of analog pointers or whatever to reconstruct the time of arrival distribution. I'm not sure if experimentalists do that in RPES, for example. There again, like what is t equal to 0? Like when do you count like the start of experiment, or how do you reconstruct the time of arrival experiment? Like I'm just curious if these like limitations apply there also, because the clearly RPES is a very successful experimental probe that compares well with theory. So I don't know how that limitation that applies to this experiment will not apply to that.
I can make a comment on that. First of all, RPES for the Quantum Foundations audience here is angle resolved photoelectron spectroscopy. So it's a method in which, a piece of solid, a pure crystal, is exposed to radiating light and electrons are emitted from the sample. And the experiment consists in measuring the time of flight of the electrons at a distant screen. And from that time of flight measurement, one reconstructs the momentum of the electron, of course, assuming that it moved along a straight line. And that again goes back to one of the semi-classical methods I mentioned. And Anirudh is absolutely right that there is really no guarantee about the t equal to 0 in this experiment, because electrons, are not coming out at the exact same time. So there is clearly a distribution of exit times of the electrons, if you want to think classically. And I must say you are in good company, because this was also the question raised by Pauli in one of his 1925 letters to Niels Bohr, where he was talking about matrix mechanics. He said, well, events in this theory don't really occur. For example, he said, we cannot talk about the instance of emissions of the photoelectrons, which are for sure observable. That's what he said. So that was my just inputs to the RPES discussion. So I don't know I mean, if it gives good results, be happy. That's how it has been going on ever since, right? So I wouldn't know how it affects, because it's a difficult many-body problem also. So that aspect is also there.
Okay, thanks. So I think we have only half an hour left, so I would like to open it up now to some more general questions. So not particularly to one of the talks maybe, but maybe more about quantum foundations in general. So you can ask to both of the speakers or comment on something. So I think
Paula, I could start with a comment, because actually I think if there are experimenters in the audience, so Siddhant, Marcus, and myself, we would really love to reach out to you to get into more discussions about experiments. Siddhant, together with Detlef, and now also joined by Marcus, have gathered really a huge amount of results, which could even be interesting, despite being a fan of one particular quantity of how the time is measured. So maybe as a general comment, this should also be something that the Laws of Nature series wants to promote: exchange between the fields, experiments, theory, mathematics, philosophy. And I think this is a nice occasion that allows maybe Siddhant, Marcus, and myself to reach out to experimentalists and I don't know, to get into discussion.
Siddhant is busy.
Well, we can do this also unofficially.
Actually, are there any hopes that you will have an experiment in some time done by some experimentalist?
No, I mean, I don't expect this to be done until quantum computers are built, I would say.
Yeah, but one has to say that, I mean, the computations that Siddhant, Detlef, and Marcus are doing, and And they are all in very, very technologically feasible regimes. So they have had, and also including myself, many discussions now with experimenters. A couple of names you saw on the slides. And I would be very positive that if there's enough interest from the community, I mean, not for saying I want to measure this and that particular candidate, but I really want to get an idea that here's an interesting experimental setup. If you only measure, a nice quantum phenomena will come out. And I think the technology is there, and the computations that these very determined and eager collaborators have done show it. Yeah, so I would not be so pessimistic. Of course, Siddhant would really love to have it tomorrow, so it will surely take a certain amount of time even to just collect the money for these experiments. But here, my appeal also to the community would be that, I mean, if we find really interest in this topic of time measurements, we should somehow hold together here a little bit and also try to get the word on the street and communicate with experimentalists and see what can be done. So not for the sake of one particular approach, but really for the sake of getting into these regimes of these nice settings where we all think we will get backflow and we'll get nice, interesting effects. So I'm quite optimistic that in the near future, then particularly in Germany, there's one group with whom we have ongoing discussions. Yeah, I mean, yeah, we are very open for this topic, and I think many other people in this field as well. I mean, you have seen so many approaches, so I think it's very the time is right now to go out and measure.
Okay, I see there is a question by Shelley, or a comment. Shelley, you want to go on?
Yeah, no, just a question to both speakers who described lots of very interesting experiments. My question is, do you expect any of these experiments to clearly demonstrate that orthodox textbook quantum theory is wrong?
So who of you wants to answer first?
Yeah, no, I was thinking, sorry, the video went off. Okay, can you listen to me? I don't, for some reason, the video is not working. But...
Yeah, we can hear you.
Okay, then that is fine. To rule out orthodox quantum mechanics, well, which means in the case of collapse model would be to really see some collapse effect. No, at least I'm not so sure with the current experiment, because even all these parameter, this exclusion plot I show are true only for the simplest model, the Markovian one. And then if you introduce also, for example, non-Markovian or dissipative effect, so even much before going to a proper theory which describes where this collapse noise comes, even sticking to a phenomenological approach, you can still propose more complex model, but not complex just for sake of making new prediction, reasonably complex. So it is reasonable that a noise has some cutoff in the spectrum at a certain energy, so it's not really a white noise, or that some dissipative effect at a certain point can play a role, and so you don't have this steady increase of energy. And with that, then still there is a large number of, I mean, many experiments which now exclude large region maybe will not exclude it so much. But definitely I think that if one can do an interferometric experiment with masses up to 10 to the power 11, well, that would be interesting anyway. I cannot claim that I have the confidence to say at that level we will see collapse, but if we see it, is the best. If we don't see it, it's still interesting, because you can know that you can push quantum mechanics to that point.
Surely it's good for you if you see it, but I'm wondering what your real expectation is. Do you really think quantum mechanics is wrong on this level of description?
Well, that there are problems with standard quantum mechanics, I'm quite confident. Otherwise, I would not work all these years.
So you're confident that really the predictions are wrong?
Yes, I'm not so confident, but we can see it. So
okay, but if you, how about? But if you also were interested and talked about some work you did about trying to derive and maybe getting some results connecting Bohmian wave function collapse with spontaneous localization. If that were to come out and work, if you could derive spontaneous localization from Bohmian mechanics, that would show, wouldn't it, that there is no possibility of spontaneous collapse models not being explained in an orthodox way?
Because on a level of prediction,
the predictions of Bohmian mechanics are surely orthodox quantum mechanical predictions.
yeah, well, yeah, I guess, well, okay, the answer is I need to think better about this, but yeah, it seems to be covered, but but still then you have this heating effect. Yeah, I mean, if you derive a collapse from this conditional wave function, then all these collapse, also the heating effect, all these indirect tests are not coming anymore from some external entity, but are really coming from just other particles interacting with your system. And then, no, I'm thinking, for example, with this experiment of radiation emission, then you will see it because the particle you're studying, the system is interacting with each other. Honestly,
I think that just highlights the trickiness of actually safely concluding, even after you do find experiments which seem to confirm, if you were to find such experiments, seem to confirm spontaneous localization in some form, seem to conflict with orthodox quantum theory. It's a very tricky matter to be sure that that evidence is definitive.
Yeah, I agree. And well.
So Siddhant, do you want to comment on this also for yours?
I'll just put my 2 cents on this. Well, I mean, as you guys just agreed, there are really no stakes for quantum mechanics insofar as the arrival time experiments are concerned. Well, I mean, all you can go out and do is check a prediction, and the quantum mechanics that you just have in mind is where you can, in principle, include the analysis of more and more degrees of freedom, which, could indirectly produce the result that you observe in the lab. Insofar as that is allowed, well, there's no way to ever tell if it's definitively wrong. But as far as the arrival times are concerned, I feel that we do have very interesting opportunity for doing these experiments that I described. And the way I see it is, of course, quantum mechanics will not be wrong, but given the empirical standards of standard quantum mechanics, it will just be less and less remembered, because it cannot produce a prediction as it used to for other textbook experiments with the same ease, as in the case of arrival time experiments. So I would see that as a place where things will head.
So I guess it would, the psychology would then come into play, as I guess it always does, unfortunately, in physics. I mean, you might have a situation where you can convince lots and lots of physicists that they have to abandon orthodox quantum theory for something like Bohmian mechanics, even though you yourself know that that's not really true, that they don't have to do that, that if they were able to carry the quantum mechanical calculation out to the end, beyond what anybody ever does, they would get the same predictions.
Right. I mean, would you agree that it's a bit like how you would compare the predictions of the epicycle theory with those of Newtonian mechanics for solar system phenomena, at least to some extent? Because there you can never say epicycles is really wrong, because you have just not done the analysis correctly enough, maybe.
It's a little bit like it, but I think it's a little bit different because the epicycle theory was supposed to be a fundamental theory. The fact that you have to do a more complicated computation here in quantum mechanics and our textbook quantum theory doesn't make the theory itself on the fundamental level more complicated. Of course, you don't need to say that. I mean, the theory itself on the fundamental level, it's not, the problem isn't so much that it's complicated, it's that it's unprofessionally vague. We don't really know what it's actually saying about the world. It's worse.
Well, for that matter, as you correctly said, it's not even a theory. I mean, Tim
Exactly.
states
Not
a
even
predictive
really a
calculus. How can you
Right.
falsify a collection of recipes? I mean, they will always taste good if you execute them right.
A collection of vague recipes.
As we saw in this arrival time situation, for example.
It doesn't have to be that vague, but of course, yeah. So yeah. So the situation is one where, I mean, not saying you should be happy to have arguments which on the psychological level will convince people, even if you're fooling them a little bit.
Okay.
Yeah,
So, yeah.
just one more comment. Now I was thinking better about what Shelley pointed out. Yeah, actually, of course, even in order to claim that you have seen the collapse, of course, you must basically be sure, and this is then also the case if you consider the conditional wave function, but you must be sure that basically there are no other sources of, for example, other interaction which cause the same effect. For example, also standard decoherence, because of then what you measure. So yeah, in this respect, I agree that it will be quite hard to see a signal and say this is the collapse, unless we don't find some much more detailed model with some very characteristic structure, but in this moment, I don't see it so easy. Okay.
Okay, so there's one further question by Christos.
Yes, well, actually, he's adding on the comment of Shelley on that one. So I would say the following: assume that you are able to demonstrate that this coupling of, let's say, the particle with some pointer states or whatever, localized states, explains spontaneous collapse. So essentially, a spontaneous collapse is an effective theory whose basis in the end is some fundamental Bohmian theory of particles that are detected and others that are not, or other degrees of freedom that are not. So then you can say, I measure, though, I do the experiments and I measure the amount of, let's say, the probability of collapse per unit time, per degree of freedom, of what? Of those degrees of freedom that are observed. So then this information, I would say, from the point of view of physics, is absolutely useful. So let's say the question here is, I mean, you have physics as a theory that explains the empirical world, and also you can have physics as a theoretical construct, ontological in nature and whatever. Here, the information that you get from such a coupling wouldn't really be whether orthodox quantum mechanics is correct, whether or not, let's say, orthodox quantum mechanics is correct, but actually you would get an information on how many degrees of freedom of the universe we are able to control through our experiments. I don't know if that point is made clear.
Okay.
Yeah.
Yeah.
Okay, so Dirk, you want to ask?
Yeah, maybe I say in a little different words, more or less the same than Christos now already told us. I would also like to ask the question in a more positive way. So not in the way, I mean, can we prove someone right or wrong, or I mean, especially if the situation is so vague that I mean, the state of the art quantum theory is for practical purposes nice, but it's really a bit vague. So, but we can ask maybe the question more positively. are there settings where we have good reason to believe that we can conduct an experiment and see a funny effect? And Christos put us a bit more professionally in determining which degrees of freedom we can control and what kind of phenomena we see. So in some sense, it's a situation where we can tell, or Siddhant and Sandro and Marcus and many of the people can tell convincing stories why we should do or conduct an experiment, and then think very hard about what kind of theory we can use to explain it. Why do we write down one or the other distribution of times, and try to make a also mathematical convincing argument out of it. So I also would say a nice angle is to somehow appreciate that there seems to be good chances to see some quantum effects. As we have seen in the last 100 years, a lot of people were looking into position-related quantum effects, and now we can look into also time-related quantum effects, for example, or these colors-related. So I think it's a nice angle also to come from the opposite side of the story. So just a comment.
Okay, so Serge, maybe you want to ask a question? You are still muted.
No, sorry.
Now it happened to me too.
I just forgot to hand on. It's okay. It's fine.
Yeah, I was muted. So it was. I had a small comment, which is related to what Shelley was saying. I want to point out the following: that so it seems to me that the majority of physicists nowadays actually have little idea of foundational questions. I mean, they don't really care. They are kind of shut up and calculate mentality. I think the arrival times point so these findings of Siddhant and Detlef and Marcus is the first time in history where the for all practical purposes really works now for the foundations, so to say, or let's say for Bohr mechanics. Because previously people were just saying, look, why do we need the second equation if for all practical purposes we just we get the predictions just like that without it. So if you analyze all those, Siddhant was listing all those approaches that were concocted to predict arrival times. If you go through the literature a bit more carefully, Siddhant didn't have time for that today. Turns out that most of them, I would even dare to say all of them, except for the Bohr mechanics, just are not general enough. I mean, you can always come up with a physical situation where this or that approach fails to deliver any prediction. And
disagree.
All right, so you may comment on that, or of course, but this just means that. So, in my opinion, any wave function complete theory that you have, if you are shut up and calculate mentality, if you are for all practical purposes, you just care to get predictions for the experiments, all those, so you have to discard all those formulations of quantum mechanics. They're just not for you. You just can get predictions in all the situations that you may be interested in from them. And the Bohr mechanics more or less the only viable options, at least to my knowledge. And as Lorenzo is now already saying, maybe there are some others. Then all right, so just leave them and then make experiments and then compare them. But already without experiments, already to this point, there are already enough reason for all practical purposes, if you are just practitioner, to discard many of the formulations. And unfortunately, in my opinion, for example, the collapsed model. That's all.
Well, I guess maybe Lorenzo.
Want to comment on this, maybe?
Could comment on this, yeah.
Sorry, I disagreed on the fact that only Bohr mechanics gives a complete account of everything. I don't disagree with what you're saying.
That also wasn't what I claimed.
You claimed, sorry, so maybe I misunderstood your claim, but I thought you claimed more or less this. So if that's not what you claim, then I don't disagree with you anymore. anyways, I was just saying that there are some of these approaches are completely general, so they can give you an answer. Not only, for example, I'm talking about my own approach. It can give you not only the time of arrival for arbitrary situations, but it can also give you a description of the measurement of time, even in situations which are not time of arrival, which I would say is pretty general and goes toward what you were saying. That's all I disagreed about, not on what you were saying. So I totally agree with you when you say that the situations that make predictions only in very limited situations, okay, that should not perhaps be taken too seriously.
Oh,
Yes,
you understood me correctly, yes.
What did you have in mind by time measurements, which are not time arrival time measurements?
Oh, for example, what time is the spin up if you have a precessing spin? That's also a different time measurement, right? So in our proposal can give an answer to that. Many other time proposals cannot.
I have a small remark here, Lorenzo, regarding your proposal, which I didn't emphasize. Just for free motion without any potentials and for a Gaussian wave packet, if I'm correctly remembering, the proposal is even not normalizable as a probability density.
Also what I wanted to point out.
Yeah, well, it depends on how you prepare your wave packet. It's not normalizable if...
No, the wave packet is a Gaussian, the no backwall experiment, and I look at the arrival time as per the formula you gave at the detector location. It's a quantity that behaves like 1/t for large time, and that's just Schrödinger evolution. It doesn't depend on the initial wave packet. You can change the initial wave packet, but the long time behavior of wave packet.
Okay, I see what you mean, because you have the
not even a
normalizable
normalizable quantity.
Packet. Yeah, sure.
So I'm a bit surprised that you said you were quite general.
No, but that's to be expected, right? Because you have that the wave packet spreads while it evolves. And so if it spreads fast enough, it means that there will always a big overlap with the detector position. So how can you normalize that?
Well, you see, the wave function was common to all other approaches, right? And they all at least gave us a normalizable distribution, so they would
sure.
benefit.
No, I'm just saying that if it's non-normalizable, that there might be a physical reason for that, and that is simply that the wave packet spreads so large, so fast that you always have a big overlap with the detector at any time, and so you cannot normalize because of that.
I'm not sure I follow you.
Because detected will be the distribution of the detection time will be normalizable.
Obviously, right? If you do n
No, because the particle can arrive after an infinite time because just simply the wave packet spreads out.
The click occurs.
Yeah, maybe after an infinite time. So in order to normalize that, you need...
And it doesn't occur at all if it's after an. But that just means that what you're computing will not integrate out to one, be less than one.
Yes, exactly.
It will not be a divergent quantity. I totally agree with Shelley, actually. I mean, that's...
you agree that if you have a particle that sits at the detector position at all times, that's not normalizable?
I mean, if you have a position in your theory and an equation for how to describe the evolution of the position, then you can even talk about where the particle sits. But if you only have a wave function, the particle could be anywhere.
Forget about quantum mechanics. Suppose that in classical mechanics, you have a particle that sits at the position of the detector at all times. That's non-normalizable, right? That's the effect I'm talking about.
Not divergent, though.
Yeah, it's divergent because at all times the particle is there.
No, so the probability of detection at finite time is zero in that case. It never gets detected, ever.
It gets detected at all times because the particle is already there and it stays there.
The detector is not going off.
Exactly. I mean,
it's always going off. I mean, the particle is at the detector.
Don't always go off. That's not how detectors behave. If it
well,
did that,
okay,
we wouldn't call it a detector.
yeah, okay. Maybe we have a different idea of how detectors behave. I'm saying that
detector. Just going to call out a detector.
What I'm saying about the detector is simply that If the particle is at the detector position, it says it's here. That's all I'm saying. So if the particle stays at the detector position, it's always saying it's here. So it's non-normalizable. That's how I describe the detector. You evidently have a different way of describing it.
I have a naive way of thinking about what's meant by detection.
Right. All I'm saying is that if the particle is at the detector position, the detector says it's here. That's all. Very simple.
But if you're talking first arrival, then also in this.
No, I'm not talking about that.
But that's what we've been talking about.
Yeah.
That's a different situation than what I'm talking.
In any case, the Gaussian wave packet could start as far from the detector as you like. In that case, I see no reason why you shouldn't have a normalizable distribution, because the particle was not on the detector at all along, right? If you buy the Bond rule of quantum mechanics.
No, but sure, that's true. At the beginning, it's not there. But since the wave packet spreads out, there's a very large component where the particle is at the detector at all times, not at the beginning, but
let me answer that as well. You can give a velocity to your wave packet as large as you please, huge velocity, so that it zips past the detector before even you blink your eye. Even in that case, the distribution turns out to be non-normalizable.
Sure, because it spreads out. It's independent of the spreading of the wave packet is independent of the velocity.
I was suggesting that you can give a very huge velocity to overwhelm the spreading for practically all.
No, then it's normalized. That I know.
But I was saying that it behaves like 1/t, the time dependence of the wave.
Well, we should do
yeah,
the
we
calculation.
can
We should discuss offline. But I did that calculation. If the speed is fast enough to overwhelm the spreading, then it becomes normalized. Yes. But maybe I'm wrong. I don't know.
No, we could discuss that. That would be nice. Yeah.
Okay, I think we should come to an end because it's already almost 7. And so thank you very much for the discussion. Thank you, both of the speakers, for coming and giving the talks. And
I'm sorry that the camera is not working. But I'm sorry the camera is not working, but thank you to everyone to being here.
It's a nice picture, Sandro.
Thank you.
So this was very nice, I think, and also the discussion. And now I would like to hand over to Angelo. He wanted to say a few words.
Yes, thank you very much to all the speakers we had, in particular the young speakers today. Thank you to all the people that participated to this series of events. So this is the last one for the spring session. Then we will get back in the fall. We will keep the same format, one pair of talks per month, starting at the beginning of October. So beginning of October, beginning of November, beginning of December, beginning of January, and then again later on with the spring session to 2022. We will give you proper information in due time. We all hope that you will have a nice summer. We'll get back to you in the fall. Thank you very much.
Thank you.
Stay healthy.
Thanks.
Thank you.
We'll see you then.
All right. Bye-bye. Have a good time.
Bye to everyone.